Hello guys, and welcome to another video tutorial. And in this tutorial, we are going to be looking at computer vision with OpenCV. Computer vision is all about making or giving our machines the ability to see. So we are trying to make our computers make sense of visual data. In this tutorial, we are going to cover the basics of computer vision using a very popular library called OpenCV. The OpenCV library is well known for its simplicity to use and its wide array of applications. This tutorial is organized into 8 chapters. 8 chapters which are organized like the chapters of a book. So I will encourage you to follow these chapters chronologically, because each preceding chapter will be the base for the next chapter. It is also worth noting that within this tutorial, I'm not going to write any code, as the code has already been prepared before the lesson. Why? Because if I'm starting to write the code during the lesson, that will take a lot of time, making the tutorial to be long. And at the end of the day, the actual message that I'm trying to pass out might not be given, because much time was spent writing the code instead of explaining. So, bear in mind that the code was pre-prepared, which does not mean you are supposed to write any code. You should always feel free to pause the video, run it, make sure it runs, make sure you understand the concept behind that line of code before you can hit the play button and continue. So, the tutorial should be followed at your pace. Moving on to the course outline, as I said earlier, the tutorial is divided into 8 chapters. The first chapter will be an introduction, where we are going to see an overview of computer vision concepts and applications of computer vision concepts, and why computer vision is so important. Why are we learning it? Chapter 2 will be getting started with the OpenCV library. We are going to be installing and setting up all the libraries necessary. We are also going to see some of the most basic OpenCV methods given to us. Chapter 3 will be image processing and manipulation. Here we are going to access and manipulate image pixels, resize, crop and flip images. We are also going to see how we can write and annotate images. In Chapter 4, we are going to be looking at video manipulation. How we can access a device's camera, how we can write and read a video. Chapter 5 will be basic image enhancement. Here we will see bitwise operations. We will also see image filtering. So here we will talk of image blurring, sharpening and edge detection. Within this chapter, we will also treat morphological operations. The next chapter, Chapter 6, will be about image thresholding. And Chapter 7, we will see image features and alignment. And the last chapter contains a project. We are going to see how we can combine some of the concepts we have learnt so far into a real-life application. The video has been made very easy for you to understand. Even the OpenCV library is very simple. That is why it is the most popular computer vision library in combining OpenCV library alongside Python. You notice that it has been made very simple and easy to understand. Always feel free to pause the video. You can rewind the video if there is something you are not getting, and if my talking speed is too fast, you can always reduce the playback speed. So, grab your cup of coffee and let's get started. Computer vision, also known as CV, is a subfield of artificial intelligence that enables computers and machines to analyze videos and images. Artificial intelligence is all about making machines to behave like human beings. There is a core sense or ability which all human beings possess, which is the ability to see. So computer vision is a field which enables systems to make sense of visual data and extract valuable information. So it's not just the ability to see, because we can argue that computers have cameras and they can serve as an eye. But the question here is to be able to make sense of the visual data or extract valuable information, like the way human beings make use of their eyes. For example, a human being can see a dog and know it is a dog, or see a lion and know it is a lion. How does one make sense of this information? When you see a lion or a wild animal, you should run. And so, this is the ability we are trying to give the computer. Visual data is abundant in our daily lives, from digital images captured by cameras, video footages from survey systems. So by developing algorithms and techniques for computer vision, we can teach computers to automatically analyze and interpret this visual data, making them capable of performing tasks that were previously only able to be done using human eyes. There are 6 computer vision concepts. Feature extraction. During this phase, the system scrutinizes the incoming visual data to identify and isolate significant visual elements such as ages, shapes, textures, and patterns. And to facilitate computer processing, these identified features are translated into numerical representations, effectively converting the visual information into a format that machines can comprehend. Normally, machines will always store information in terms of 0 and 1. So in feature extraction, we just have to identify some key features or areas. For example, a circle has no pointed edges, while a square has 4 pointed edges. These are some features that enable the computer to make sense of a particular image. So if the computer sees an image with 4 edges, it will conclude that it is a square. It does this by identifying various patterns and converts it into numerical representation. That is in the matrix format because the computer understands only figures. Object detection. Here we identify and locate specific objects or entities within the images. This enables the computer to not only detect the presence of objects, but also understand what those objects are and use them as applications in various fields. For example, it is not just a matter of the computer identifying that there is a square in the image. The computer should be able to identify all the objects in the image and make sense of what is happening. So the square might still be a car, depending on how you're going to combine the square part of the car and the round wheels. So objection detection is all about combining all the features in an image and making sense of it as a whole. Image classification. Here we use a machine learning model. It involves categorizing entire images into predefined classes or categories. Convolutional neuron networks, which are a specialized class of deep learning models designed explicitly for image-related tasks. They actually excel in finding patterns in making highly accurate image classification. Once you've made sense of all the objects in an image, it is time for the computer to tell you what exactly the image is. For example, if you have a dog and a cat, it will take them and try to identify all the edges and patterns, and from that can identify certain objects like the ear, eyes. When it combines all of them, it will be able to associate these images to predefined classes. Object tracking. This involves the ability to monitor and trace the movement of objects as they traverse through consecutive frames of the video. Semantic segmentation. This is a technique which takes object analysis to a whole new level. It does this by labeling each and every pixel within an image with its respective category. In simple words, it is all about a higher level of image editing. In short, it is all about taking image analysis to a whole new level. Application and leverage. This is a combination of all the concepts into a real-life application, which one can sell for people to use and appreciate the computer vision concepts. Take a while and think of the importance of your eyes. Think of how life would be if we never had eyes or we could not make sense of visual data. That alone gives you an indication of how important visual data is, and if you translate that into the field of computer, you will see that there are several applications of computer vision. Some have already been discovered, some under research, and some are still to be discovered. It is a field which is actually going to revolutionize the world. Some fields which have been mostly affected by computer vision are healthcare. Computing vision has been used in medical imaging, aiding doctors and researchers in diagnosing and understanding complex medical problems. For example, cancer cells which are outgrowths. An apt cure for cancer has not yet been developed, and at most times, it is usually noticeable when it has been chronic or when it has infested a large amount of cells. Cancer cells are always likely to go undiscovered at the early stages because they are so small and the facilities available are not efficient for spotting out cancer at the early stages. Imagine a situation where a computer or a machine could actually see the cells and make sense of it. That is, see cancer cells and know that they are cancer cells. Which takes us back to the concepts of computer vision, which we will notice that feature extraction and object detection. Based on features, edges, and patterns, a computer will be able to identify normal cells which are supposed to be there. Now, if it sees another cell which does not follow the pattern of the other cells through image classification, the computer will be able to detect that this is a cancer cell, no matter how small it may be. Looking at this scenario, you would notice that there will be no abnormality in the human system that will go undetected, so long as the lens or equipment used can actually locate these tiny cells. With this alone, complex medical problems are going to be easily solved. Even in the case where the computer will not know whether it is a cancer cell or a harmful cell, it can raise an alert and the doctor can come and look at it and perform specific tests to identify the cells. Automotive industry. Computer vision enables autonomous vehicles to see their surroundings, ensuring safe navigation on the roads. For example, self-driving cars. The concept of self-driving cars is that the car will drive on its own, but I don't believe a car can drive on its own if it cannot make sense of its environment or see its environment. So with the cars being able to see its surroundings, it will be able to see another car and know that it is another car. So depending on the distance between the other car, the car will brake or accelerate or turn left or right. If the car moving, when it identifies a curve or a bend, it will know it has to turn left or right and not move straight forward. All these can be made possible only if the car has been equipped with a system that permits it to make sense of its visual surroundings. We have other applications like survey systems, like in movies, where there are cameras placed in the hallway and based on the way that the person moves, it can detect if the person is an imposter or a stranger. There are security systems where 10 meters away from a person's house, the security system of the house can detect whether the person is a stranger or non-guest. These are a few of the applications of computer vision. And hopefully by the end of this tutorial, we're going to be able to work on our own project to see how we can make use of what we know or what we are going to learn so far in solving a real-life problem or making a project which you can actually add in your portfolio. In the next lesson, we are going to see how we can get started with our OpenCV library. And with that, we are going to start with our installation and setting up the library. So get ready. We will start coding soon. See you in the next lesson. Hello guys, and welcome to chapter 2 of our computer vision tutorial. In this video, we are going to get started with our OpenCV library. The first thing we need is Anaconda. You can head over to anaconda.com/download and it will take you to the download page. Anaconda is basically a distributor or a set of tools that is very familiar among data science lovers, machine learning, engineers, and everything. This is because it assembles a group of libraries which you can download and use, and it will be very useful in data science and machine learning related work. So we are going to be using Anaconda as our IDE or distribution. It is a free distribution to install, and it has thousands of the most fundamental data science, artificial intelligence, and machine learning packages. While downloading, the software automatically detects the operating system you are currently running on, and it indicates by showing you this icon here. So I'm running on a Mac. That is why you see this Mac logo here. When you click on download, for Mac users, they are going to ask you if you are running the Intel OS or the M1, M2, M3 OS. So I'm running the Mac Intel OS version. So I'm just going to click on it. With Windows, when you click on it, they're going to ask you which operating system you are using. So you just virtually need to know which particular operating system you are using and click on it. And if they don't ask, the download will just launch. So I'm just going to click on Mac Intel and my download has started. And you're going to be redirected to this page telling you, thank you for downloading. So I already have this installed. So what I'm going to do is that I'm just going to run it. And basically you don't need to bother because it has an installation guide which is going to take you through the installation process. And it's virtually a matter of clicking next, accepting the terms and conditions, and next until you install. So it's actually very easy to install and has a very self-explanatory installation guide. So I'm going to run my Anaconda Navigator, and it usually takes some time to load. So we are just going to be patient. When you finish doing everything, this is how your navigator should look like. The next thing we are going to look at is how we can install our OpenCV library. Before installing our OpenCV library, we need to create what we call a virtual environment. Okay, here they are telling me that there's a new version of the navigator available. So I'm going to have to update that, but not now. So we are going to look at how we can create a virtual environment. But before that, what is a virtual environment? A virtual environment is simply an isolated container where you can store specific project-related files. And this environment is important because dependency management. It provides a way to manage dependencies to different projects separately, and each virtual environment can have its own set of installed packages without interfering with each other. Reproducibility. This is where virtual environments enable you to reproduce the exact development environment across different machines or different developers. In essence, just look at a situation where two people, for example, A equals John and B equal Mary, are working on the same project, and both of them are running different versions of Python, where John is running 3.12 and Mary 3.10. Difference in versions always come with difference in packages. So they might be using a method which is different in both versions. What happens is, when Mary writes her own Python and sends to John, it will not run on his machine. Why? This is because Mary is using code that is expired, or not accepted by the new version of Python John is running. So how can this situation be amended? By the use of a virtual environment, because you can create a virtual environment. It is an isolated container, so it's like computer or a setup on its own. So in that virtual environment, you can install a certain version of Python. For example, Python version 3.9, and any project within that environment will use Python 3.9. So even if that environment was to be used by John in his machine, he will be able to work with that project, so long as the project is within that environment. That's what it means by a virtual environment can have its own set of installed packages without interfering with each other. Your machine can be using Python 3.12, but you can run an environment that has Python 3.9, and so long as the project is within that environment, it will work fine. In this way, it is easier for two people to work on the same project. If John makes changes, he will need to send the project inside the environment to Mary, and both of them will be able to work on the same project easily and without any worries. Enough of the theory. To create an environment, there are usually two ways. You can go through the terminal, or you can just use the navigator. Since a graphical user interface is meant to make life easier for us, we need to see how we can create a new environment using our navigator. So over here, you have Home and you have Environments. We will click on Environments, and when it opens, you will see all the environments you have in your machine. So this base root is like a global setup of your machine, and this Anaconda 3 is an environment that comes when you install Anaconda. What happens is you can create an environment. Down here you have Create, Clone, Import, Backup, and Remove. If someone wants to give you an environment with the project, he will give you the complete files and you will have to import it. So we want to create a new environment. To create a new environment, you click on Create and specify the name. We can just have new_env. If you're working using Python, you can check on Python. If you're working using R, you can check on R. What happens is that the computer or navigator just detects which language is installed in your systems. I don't have R, that is why R is blurred out. Here I have Python, and it allows you to choose the version of Python you want to use. In my machine, I'm using 3.12, so even if I take 3.6, the project remains within this environment. The project will work fine. So this is an advantage of using a new environment. So I'm going to take 3.12.2, which is the latest, and we are going to click on Create. When you click on Create, some things are going to be loading. Ideally, I will want you to call your environment OpenCV_env. You will need to create your own environment, and you will give it a very descriptive name. So we will just call it OpenCV_env. After creating your environment, you will see it appear like this, and you will click on it. And the icon, which looks like a play button, should be on it, and it tells you which environment you are currently in. Now that you are in the environment, the next thing is to download our OpenCV library. You click on Not Installed above and search Packages. You're going to type OpenCV. And currently, you're not going to see the OpenCV library here because I already have it. But this is how it should be. OpenCV, Computer Vision, and Machine Learning Software Library 4.6. So mine is going to appear under the installed filter, but you're going to have yours under not installed. What you do is you check on it, and you'll see Apply pop up below. When you click on Apply, it is going to download the packages automatically. After doing that, how do you check if the package is installed successfully? You click on Home, and since it is a new environment, there are many things here which will not be installed, like Jupyter Notebook. So when you come to Jupyter Notebook, you will see Install. You click on it and it will install everything for you. The button will change to Launch. When you launch Jupyter Notebook, it will run by starting the terminal and your browser will open directly. So this is how your interface will run. This is the latest Jupyter interface. In order to test if it has been successfully installed, we can go to the desktop when we create New Notebook. Having created a new notebook, we will import CV2 as CV. So the CV is the CV library. We will run cv._version_, and we should get 4.6.0. It should correspond to the version we saw when we were about to install it. Now we are sure our OpenCV library is running. Anytime you want to use OpenCV, you have to make sure you are running the environment that contains it. So make sure you are running the OpenCV as core environment in your virtual environment. And if you change the environment to maybe default or base, you will not be able to run OpenCV. So if you type in the code we just typed, it will give you an error. Anytime we will be working on OpenCV, make sure you are in this virtual environment. In the next video, we are going to get started with OpenCV library. Welcome to another video in our tutorial. In this section, we will get started with images. Image manipulation is one of the most basic functionalities which OpenCV gives us. In order for us to be able to detect objects, edges, faces, and the rest, we need to be comfortable around images. We should be able to read an image, check its attributes, convert the color channels and everything, and save the images. I already have a notebook prepared for us. OpenCV actually has an academy or university where they give you some documents which you can use to facilitate your journey. And this is one of them. We are going to go line by line and explain everything so that you understand. The first thing we have to do is to import the libraries we are going to use. We are going to import CV2, which we saw in the previous video, and it is the OpenCV library. We will import NumPy, which is a Python library which enables us to work with large number representations. When it comes to working with matrices, as we know, images are matrices. Converting an image to a format the computer can easily understand, we convert it to matrices. Since the matrices are so large, using normal mathematical functions might not be really efficient. So NumPy helps us with that. We will also import matplotlib, which is a library that allows us to make graphical representations, visualize data. We also have ipython.display, which enables us to display images from our code. We will run this line. It will load for some time because it has to import libraries. The next thing we will see is how we can display images using this image function or method, which we imported from ipython.display. If we run this, as you can see, this is the image checkerboard _18*18. You have to know that for all the images, this is the path to the image. so the image must be in the same folder with our notebook. As you can see, it is getting started. If it is not in that very folder, you will need to include a full path. If you don't include a full path, it is going to return an error. We are going to run this next line. This image here enables us to view the image directly within our notebook. This 18*18 is virtually the size. That is 18 pixels by 18 pixels, and also 84 by 84. That explains why this image is different to that image. The next thing we'll be looking at is how we can make images using OpenCV. OpenCV allows us to read different types of images. There are many types: JPEG, JPG, PNG. OpenCV virtually allows us to import or read tons and tons of these images. You can also load grayscale images, color images, and images with alpha channels. Grayscale images are black and white images. Color images are the images we all know with all the colors. Images with the alpha channel. The alpha channel here controls the opacity. That is how transparent a particular image is. You might have viewed websites where you have an image and the image is kind of transparent, so you can see what is behind the image. That is controlled using the alpha channel. You usually see something like RGBA. The A is the alpha channel and is usually in a scale of 0 to 1. It can also be in percentage. To read an image, we use the imRead method. This imRead method is called by the CV2 object, which is from our OpenCV library. This imRead method takes 2 arguments, but 1 is required. So you must specify it. And that mandatory argument is the path to the image you want to read. This image here is a different function, but it also takes a path. That is the same thing that happens with the input method. You need to specify the path to the image you want to read. And the second argument, which is optional, is the flag. The flag will tell the compiler which mode you want to read. Like I said, we have the grayscale, color, and unchanged. If you want to load the image to a black and white format, you will specify cv.imread_grayscale. This is an attribute which tells the imread function to load the image in black and white with the grayscale format or mode. We also have the imread_color attribute, which will tell the imread function to read the image in color format. And in this color format, the alpha channel is going to be neglected. If you had an image which was somehow transparent, if you read it in the c2.imread_color using this flag, the transparency is going to be neglected. So you will have the full image. And we also have the cv2.imread_unchanged attribute, which tells the imread method to read the image in an unchanged format. So the way the image is the way you are going to read it. So if it had a certain opacity, let's say 0.5, it is going to be read in that format. Since the creators of OpenCV were so generous and kind, they noticed that using these attributes may be difficult to remember. So they came up with integer representations for these flags. Instead of specifying cv2.imread_grayscale, we can simplify pass in 0. It is going to load the image in grayscale. If you want to use the cv2.imread_color, you can simply use 1 and it will load the color image. Like we said, any transparency is going to be neglected. We also have the unchanged, which can be represented using -1. Since it is optional because it has a default flag. The default flag of the color image. Because most times we want to load the color image, it is on very few occasions that we want to use the grayscale or we want to work on an image using the alpha channel. As we said, the imRead method has 2 arguments. One which is required, so one must be passed, which is the absolute or relative path. The second argument, which is optional, is the flag which tells the compiler the mode in which the image is going to be loaded. And the default flag is going to be 1, which corresponds to color image. Let's see how it works here. I have the cv2.imread. Here we have passed checkerboard _ 18 * 18 pixels. We are going to rate this and store in a variable called cb _ img. Here we have written 0. This 0 tells us that we are going to load it in the grayscale mode. Subsequently, we are going to talk about color channels, and we will understand how these color channels are represented using matrices. Now that we have called this method, we have passed the image to the cb _ img. We can run this. It represented using matrices because, as we said, the computer will not interpret the image as an image. It has to be converted to a numerical format. And that numerical format is going to be an array of arrays. As you can see here, you have 0. The 0 stands for low intensity and 255 stands for high intensity. So 0 is black and 255 is white. Depending on how black a particular portion, it's going to be closer to 0. And depending on how white a portion is, it's going to be closer to 255. If we look at this 18 * 18 picture that we loaded up here, we can see that we have black, white, black. That is why we have 0-255-0. You can see that this square is white and the other is black. That is because we are representing it in grayscale, and that's why we have just one dimension here. Subsequently, we will talk about color channels. Every image has attributes, and the most important attributes we are going to be seeing is the shapes. The shape is just telling us the size of the array that we have. That is the dimension of the array. So if I run this cell, we are going to have 18 * 18, which corresponds to this. So if I were to head over here and load 84 * 84 image, we have a problem. Let's check the name. It was .jpg, so we can change this format here to .jpg. Since it is larger, they have compressed it. That's what the 3 dots mean. What I want to show you is that the size 84 * 84 is the size of the actual image. So the bigger the size of the actual image, the bigger the shape, or the bigger the dimension of the image. The data type of the image is integer, so you cannot have 0.1 or 0.2. You will have 0, 1, 2, 3, 4. That's basically what I wanted to mention. We can just go back to having 18 * 18 and we run again. Since 18 * 18 can be displayed here, there is no need to compress it. And if we come here, it will change back to 18 * 18. The shape is just the dimension or size of the matrix representation of the image, and the data type is the type of each value. Now we are going to see how to display images using matplotlib. With matplotlib, we have plt.imshow. It is a very simple and straightforward method. When you run it, you have this. So now you will notice that with matplotlib, it will take the matrix conversion and give it back to us in the image format. With imshow, you will not have the matrix representation again. It will take the matrix representation and give us the actual image. But now you must have noticed that this was the image that we had here with black and white. But when you come here, it looks purple and white. Why? This happens because even though the image was read in grayscale, it will not necessarily display in grayscale. Because this is not the imread, this is imshow for matplotlib. So we need to tell matplotlib which mode we want to read the image in. And this is where the CMap attribute comes in. We need to pass in grey in the CMap. It will tell the method that we are loading a grayscale image. When we run this, we have our actual image the way it's supposed to be. We will have another example. We will read another checkerboard, but we will make it a bit fuzzy, so it's not going to be as uniform as this. We will run it. Now you see that the numbers here vary. So it's not just black and white. Some will be grey, some will have a lighter shade of black. What you have to know is that the closer it is to a real black colour, it means the number is close to 0. And the closer it is to pure white, it means the number is closer to 255. If, for example, I were to look at this cell here, this particular cell where my cursor is currently on, you will see that this is more of a grey. So we are expecting a value in between 0 and 255. Or I can say it corresponds to this 134, because this 134 is quite in the middle of 0 and 255. That's why it's really grey. But if you come to this cell here, you will notice it is closer to black than to white. That's why it's 233. We can now work with color images. With color images, we will use our image method form IPython to display it to see how the image is. Here we have Coca-Cola image. And now we want to read and display this image. We want to read the image the way it is in a color format. We are going to use our imRead method here, where we will have the name of the image and we will pass in 1. The 1 tells us that it is a color image. Say we want to discard any transparency, if at all there is. We are also going to print the shape and the data type. So here we see that the image size is 700, 700. And here we have 3. If we head back here, we will discover that we had image size 18 by 18 and there was nothing. Why? This is because it is 1. And when it is 1, it doesn't show it. This 3 here is trying to tell us that it is a 3-dimensional image. So what happens is that we can have this matrix and have the same matrix on top of it and have another on top of it. So we have 3 channels: red, green, and blue. With the grayscale channel, we were tracking how black or how white an image or the pixel will be. The higher you go, the closer you are to white. And the lower you go, the closer you are to black. That is for the grey mode. When you come to the color mode, we have 3 channels. One measures how red the pixel will be, another measures how green the pixel will be, and the other measures how blue the image will be. When you take one channel and put on the other one, you will see that the pixels for the three channels are going to mix to form a color. It's almost like you take your paintbrush and take out a red color and paint on your paper. Then you take a blue color and paint on that same spot. And also take a green color and paint on that same spot. When you combine all, it will give you a different color. This is how the color channel works, and it is going to be three-dimensional because it will have three representations. The first one will measure how red it will be. When it is 255, it shows it is pure red. If it is 0, it is black. If it is around 125 or 110, it is a darker shade of red. The second channel measures how green it will be. The third channel measures how blue it will be. If the first channel we had 255, the second channel we had 255, and the third channel we had 0, it means we are basically mixing the red and green color, which will give us a yellow. We will see how all of these will work subsequently. But this is just a summary of color channels. We note here that when reading an image in the color mode, you will have this 3 here, which tells you that it is a three-dimensional array, and with the data type, it is going to remain an integer. So here we will use the IMShow method to read the image, and you can see that the image is blue. There is a problem because the actual image is supposed to be red. There is no Coca-Cola, there is colored blue. The problem here is that while our IMShow method, because with the color channel, especially RGB, that is the normal order for our color channel. But in the case of OpenCV, it is reversed. That is, we have BGR. So the normal image you will get with the RGB, when it is passed to OpenCV, it will read it as BGR. So the first channel is not going to correspond to red. It will correspond to blue. Green will remain green, but blue will be interpreted as red. That is why, looking at this image, we have BGR, meaning the last channel is 255. So the first chapters with BG and R, where the B is going to be 0, G will be 0, and R, the last channel, will be 255, which explains this pure red color. But now, when we want to read the image with IMShow, it reads it as RGB. So the first channel, which was 0, will correspond to red and will remain 0. G was 0 and it remains 0. Then the last channel, which is interpreted as red by OpenCV, will be interpreted as blue. That is why the red has been switched to blue. It is worth mentioning that OpenCV works with BGR color channel format, while the normal image format is RGB. So before you want to read the image, you have to reverse the channel. And this is a quick line of code which will help you do that. You run the code. Now you see that it has reverted back to the normal color format. So always know that OpenCV stores images in a BGR format and not the RGB. Anytime you get an image, think of a swap. Now we have our image displayed in the normal red color. The next thing we can do is to split the color channels. We can split them and modify each channel individually. After splitting them, we can merge them back to form the actual color we have. In order to do that, we start by reading an image. Here we have new underscore Zealand underscore lake dot JPG. And we're reading it using the IM_read color. So we will discard any transparency or alpha channel. Now we use the split method. The method takes the image, which we have just read, and it returns 3 values, which we will store in 3 different variables. Remember, we'll read OpenCV in the BGR form. The first channel will be blue, second will be green, and the third red. Now we can decide to display each channel differently. Of course, we are using the CMAP equals single quotation grey, single quotation to display. So everything will be grey. So you will not really see everything. But now we are going to mark the intensity. This is the red channel. So where it is dark, we can say that it is red and white. So we just have to look at it that way. For the green channel, where it is darker, it means there is more of green found in that area. And where it is lighter, it means there is less green found there. So when you look at this image, this is a combined image of the 3 channels to form the actual image which we are displaying normally, not using the real map, since it is the actual image. And we do this using the merge method. The merge method takes a tuple of the blue, green, and red individual channels. This BGR corresponds to the split color channels that we had from this method, and after displaying them, we can just merge back. We create a tuple. That's why we have a bracket here. We have the BGR. We can now display it using our IM_show, and this time we don't specify the color map to be grey. That's why we have the actual image. Now we also see how we can convert to different color spaces. Here we have our CVT color, open bracket, close bracket. You see that OpenCV is a very easy library to use because the methods are direct, with no complications. So you just use the method with the corresponding argument and it will work fine. This method here converts an image from one color to another. We need to first specify the order of the colors, whether RGB or BGR. The default color format of OpenCV is referred to as RGB, but it is actually BGR. It is reversed. When you have an image which is RGB, most images are RGB. When you will be manipulating it using OpenCV, you have to take it with an OpenCV so it looks like BGR. So always mention the order of the channels, or you will have to convert it. This method takes the source. The source is the path of the image. This code is a conversion that you want to perform. The code is like a flag, the space conversion code. You will use the code to change from BGR to RGB. There is a link to documentation where you can see all the color conversion codes. You can visit that. We have a list of all the codes and their various conversions that you can use. We have BGR2, BGRA, meaning we want to add an alpha channel. You can take time to look at all these. With this one, we are reading an image. Since we are reading the image in BGR, we want to convert it to RGB and display it using IM_show. If I run this, we have our image here. We can try something here. With this conversion code, it will reverse it back. That is, change it to RGB. That's why when we converted it, we stored it in this variable img_nz_RGB. And when you print it, you will have the actual image. We have other color spaces like HSV, which is Hue Situation View. This is how it looks like. You can study this color space. It is not usually often used because the most popular space is the RGB. You can take time to look at how the HSV works. You can now modify individual color channels, so you can split them and make certain modifications to the red color channel. Then you merge back and see the difference. We have made certain modifications to the hue channel. And when you merge back, you will see that the color will change. After doing all the manipulations that you have done now, you can save your image. To save your image, you use the imWrite open bracket, close bracket. The imWrite method takes two arguments. The first is the file name, and the second is the image which you want to save. In this case, there are no flags. Now we have the name, which is the name you want to save the image in. I can do this as 3. This image we are trying to look at here. We are saving this image. This img underscore nz underscore bgr is the image, and the image is in the blue, green, red format. We want to save that particular image, and it will represent. Since it is BGR, and it is inside the OpenCV, there is no color swap. But if we try to print this using the matplotlib imshow, we will have the reverse. This already proves that we have saved it correctly, because if we didn't, we would have had an error. If I were to have 4 here and I print it, it will give an error, because saved underscore 4 does not exist. But if I come here and save it as 4, it is displayed. We come here and we can see that it has been saved within the particular folder. So after doing that, you can now read the image again, and you have shape and everything. Here we read it as a color. That's why we have the 3 color channels, and here we have read it in the color space format. That's why we have 1. So when there's 1, they don't bother showing you. This is the end of the first experience that we have had using OpenCV. In the next chapter, we will look at more complex operations, which we can do using the OpenCV library. See you in the next chapter. Hello guys, in this chapter we are going to be covering basic image manipulations. We will see how we can access and modify or manipulate image pixels, how we can resize images, crop them, flip and perform some basic image annotations. So let's get started. As we saw in the last lesson, we agreed that computers store images in a numerical format. So whenever you pass an image, it gets converted into a numerical representation, which is what the computer stores or what the computer will recognize. This image representation is what we call the matrix. A matrix in a computer or programming terms can be referred to as an array of arrays. So, we saw in our previous lesson how we could read images and display them. So over here, we are going to now read this image. This checkerboard underscore 18 x 18. So, this is like the dimension that has been attached to the name of the image. So we're going to read this image and we are going to display this image. We start by running this cell, where we import all the necessary libraries that we are going to use. So we head over here. What happens when you read an image? When you read an image, it is first going to be stored in the matrix format, which is what is given to the computer. But the computer can convert an actual image into a matrix and the matrix back to the image. So, When we use the matplotlib function here and we run it, we have the actual image. So what this matplotlib function does is that it converts that matrix which the computer has stored into the image which the user can recognize. But now, if we were to just print the variable, this variable here that stores the image, what are we going to notice? We have a matrix representation of that image. And as I said, it is an array of arrays, and usually an image is actually an array of pixels. You can think of a pixel as the smallest unit of an image, and a pixel is represented by each of these values that we see in this matrix representation. And it makes sense because you know 0 corresponds to pitch black and 255 corresponds to white. So if you look over here, the first cell here is 0, which is black. And if you come here, you see that the first cell here is also black. If you move 7 steps to the right, you're going to see that we have a 255, which also corresponds to this. So, you notice that this is a checkerboard where we have squares alternating black and white. So you see over here that this is black because it is made up of zeros which correspond to this. Then the next square here is white, which has a square made up of 255. Then we also have this corresponding here. So the computer can convert matrix to image and image to matrix because we saw here that we are reading an actual image and it was converted to the matrix, which is what the computer stores. So the computer does not store the image in the PNG format or JPG format. It converts it to a matrix. And now if you want to access individual pixels, we want to modify individual pixels. How are you going to do that? You do that the way you're going to modify elements of an array. So, we are going to use indexing, indexing. And since we have an array of arrays, that means we have rows and columns. So if I come back here, you notice that this is going to be the first row, which is row 1. And this is going to be the first column, which is going to be column 1. But bear in mind that in Python or in array indexing, we don't start with 1. We start with 0. So this first row here is going to be called row 0. And this first column is going to be called column 0. And we come here, we are going to try to print it. But before we print it, let's try to get the values on our own. So here we have row 0, column 0, which is going to be row 0, column 0. So the intersection is the value that we want to access, which is 0. The second one was row 0, column 6. So we have row 0 here, column 6. We have row 0, 1, 2, 3, 4, 5, and 6. This is the 7th column, but since we are starting from 0, it is going to be column 6 and 0. So we have 255, which corresponds to what we have in this cell, 0 and 255. So how do we modify the image pixels? So what we're going to do is we're going to create a copy of the matrix representation that we already had using this copy method here. So it creates like a virtual instance, not an instance, a virtual copy of an array. So we'll create a virtual copy. Now what can we do? We can just simply store it in another variable and perform the modification that we want to perform. So over here, I want to set column row 2, column 2 to the pixel value of 200, row 2, column 3 to the pixel value of 200, row 3. So we're just trying to extrapolate a square, and the value is going to be, the pixel value is going to be changed to 200. So what we want to do is that we are just going to extrapolate a small section, which was, let's say, row 2. So this is 1, 0, 1, 2. So we have 2. So we are going to cut this part here, and we are going to change all these values here. This one, this row 2, this row 2, column 2, row 2, column 2, row 2, column 3, row 3, column 2, and row 3, column 3. So this is the square that we are going to try to modify. So we are going to do that by changing each of these zeros to 200. And it's going to represent a small section of this row, black square here. So we are expecting to see a small change like this in the image. So we run, and what happens? We have this. So you see that thing has changed. And on the image now, we have a small grey square, which corresponds to this. So if I was to change this to 255, and ironically, you're going to notice that here, it is now completely white. So this is method 1. Another way of doing this would just be by using this shorter method, and it's going to give you the same result. So when we did that, we printed using our IMShow method, and it gave us this here. So that is it about modifying image pixels. We'll see you in the next video. The next thing we are going to see is how we can resize an image. Resizing an image is like zooming an image, scaling up or down. So resizing is increasing the number of pixels an image has. For example, we had our checkerboard with 18 by 18, and if we were to scale that image by 2, we would have an image of 36 by 36. Now there is something called scaling an image while maintaining the aspect ratio. We will see all of that. So, OpenCV gives us a method called resize. And this resize takes some parameters. The first parameter here is the source, which is the input image, the image that we want to resize, and the second parameter is going to be the size. That is the output image size. Since we are trying to be size, in order to have an unexpected size that we want to come out with, so you're going to pass that as the second parameter. Optional parameters here are going to be fx, which is a scale factor along the horizontal axis. We have fy, which is a scale factor along the vertical axis. So there are several methods or ways of scaling and resizing an image. The first way of resizing an image is going to be using the scale factor fx and fy. So what this does is that it just multiplies the number of pixels on an axis by the corresponding scale factor. So what am I trying to see? Let's come here. We have, okay. So what is going to happen is that this is the output language. But before we come to that, let's print something here. Okay. So I was trying to print a shape, but I got confused with the size and everything. So our input image has the shape of 200 by 300. So there are 200 rows and 300 columns. Right. And when I run this cell and I try to print, this is our output image, and I print its shape. So what happens is that we have 400 by 600. Why this? Because we have multiplied both axes by 2, right? Okay, let's dissect this code. This fx here controls the horizontal axis. The horizontal axis is measured by the number of columns. So if I change this to 1 and I run, what was going to happen? You notice that the number of columns here remains the same because the horizontal scale value is 1. So it's going to remain that way. So we're going to take the number of columns multiplied by 1, which was 300 times 1, which gives us this 300 again. And if I also take this by 3, what is going to be the answer? It is going to be 900 because we have taken the number of columns times 3 to give us this 900. So we will talk about fx is the x-axis, which corresponds to the number of columns. Because when you have this is an axis here, this is the x-axis. So to know how far this x-axis is, you're going to cut through it. And as I cut through it, what happens? You're creating columns. So that is why the x or the horizontal axis is going to be the number of columns. Same thing with the y-axis. The y-axis is measured by the number of rows. So if I was to take this to 1 and I run it, we're going to see that the number of rows remains the same. Because when you multiply it by 1, it will remain what it was. And if I also take this by 3, what happens? It's going to be 200 times 3, which is 600. And if I run it, we now have our image, which has been resized. So it's no more having the 200 by 300 shape. It's now having 600 by 900 because we have multiplied it by the scale factor of 3, both x and y axis. Now we're going to look at a second method. The second method is by specifying the exact size of the output image. So here we are going to use scale factor, because with the scale factor, I just need to specify a certain factor and it does the multiplication itself. But now I want to tell the computer, okay, I want the image to be this particular size. So I'm going to pass a dimension of my choice, and the dimension is usually a tuple with x and y. So here I'm going to have my desired width to be 100, my desired height to be 200, and I'm going to create a dimension that is a tuple of 100 and 200. So if you run this, what happens is you now have an image with a size of 100 by 200. So if I was to change this here to 500 and I run, you're going to see a noticeable change in how the wide image is going to be, the x-axis. So you see that now it is longer. Yeah, I'm actually telling you the exact size that I want the output image to be. The next method here is going to be resizing while maintaining the aspect ratio. So to resize while maintaining the aspect ratio, we are first of all going to have our desired width, right? And to get the aspect ratio is usually the width divided by the height. So it's the ratio of the width to the height. That's what makes up the aspect ratio. So to resize an image while maintaining aspect ratio, you need to get the ratio of our inputs to output image, right? Okay. If I have, for example, if I want to have an image with a desired width of 100, what happens is that I need to get the ratio of that desired width to the actual image. How do you get that? You get that by dividing that desired width by the rules. The number of rules in our actual image, you get the shape, and you can now get the number of columns. It's actually columns because when you talk about horizontal axes, we always talk about the number of columns. And the number of columns is index 1, because the shape method returns our x and y axis. Right? So the shape usually returns something of this sort, where we have the x and the y. So the y is at index 1, because remember, we always start counting from 0. So this is index 1. So that's why I'm getting the shape at index 1, the number of columns. And it's going to be divided by the width of our desired width. So well, that's now how we get the aspect ratio. Now where we get the aspect, we have got no aspect ratio from the width, right? Now we also want to get it according to the y-axis or the height. So we already have this aspect ratio. What happens now is that we can just multiply the height of the input image by that aspect ratio. Because the aspect ratio actually is more of like, is the ratio of the width to the height. So you have an image of 100. If I have an image that has a width of 100 and a height of 200, the aspect ratio is going to be half. Right. So if I want to resize this image while maintaining the aspect ratio, I need to make sure that when I finish resizing it, when I resize the image, the ratio of the width to the height should remain half. So if I was to resize it to maybe 400 in width and 800 in height, so you discover that 400 divided by 800 will still give us half. So I've actually resized it while maintaining the aspect ratio. But if I was to resize it maybe to 400 width to 600 height, we discover that it is going to be 4 over 6, which is 2 over 3. That's 0.66, which is not half. So we have not maintained the aspect ratio. So to maintain the aspect ratio now, to get our desired height, we need to multiply the number of rows. So the number of rows now measures the height of the image. So I'm multiplying it by the aspect ratio which we got above, which was the width, the desired width divided by the number of columns. So we're trying to maintain them, and when we have had this now, we now have our actual dimensions of the output, which we are going to pass in our resize method, and we are going to print, and we see that we have maintained the aspect ratio. So you notice that in the above methods here, for example, we had this in the first method here, where we were using scale factors. We just go out and we don't actually maintain the aspect ratio. We don't, because 200 here divided by 300 is 2 over 3.0.67. And if you have divided 600 by 900, that is, I think. Okay, yeah. The aspect ratio here was maintained because the two are going to give you the same ratio of 0.67. And we head over to the second method here. We notice that the aspect ratio is not going to be maintained here, because here we have 500 divided by 200, and our input was 200 divided by 200 by 300. So the aspect ratio is not maintained. So that's why here it's always essential to calculate it. So with the scale factor, we can be quite sure if the two scale factors are the same, then we are sure that we are going to maintain the aspect ratio. Because you saw above here, both scale factors were 3. So indirectly, the aspect ratio is going to be the same. But when we come, if the scale factors were different, the aspect ratio is going to change. And here, if you wanted to use maybe this method where you are specifying the output shape, we need to make sure you perform this calculation to make sure that both axes, or both the rows and the columns are increased in the same proportion. So the rows should not be increased by a certain number, and the columns are increased by a different number. That will now disrupt the aspect ratio. So that is how we receive an image while maintaining the aspect ratio. The next thing we will see is how to crop an image. Cropping an image is basically selecting a particular portion of an image. So if you were to take a picture where you were standing and there was a cat by you or a bird in the sky, and you want the picture to contain only you, what you can do is you can select a portion of that picture which has your face or the object of preference, and the other parts of the image are discarded. So that's what cropping is. In order to achieve this, we basically use the crop method. Here we will read a new image, as you can see here, and we will convert the color channels so it will not be RGB, because RGB is the original format in which the image comes. But since we want to manipulate it using OpenCV, we can convert it from BGR to RGB. Because we read it using OpenCV, so the color channel is in BGR. We want to show it using matplotlib, so we need to convert it from the BGR to RGB. So this is the line of code which we saw last chapter. Basically, where you see -1, it tells you we are reversing the order. We print our image. Now we want to crop a portion of our image. We saw that an image is represented in a matrix form. The way you can access a matrix, you can also slice a matrix. What is slice? Slicing is basically creating an array out of an array. So you specify certain boundaries or borders and discard the rest of the array. That is what slicing is. And the way we were able to edit an array using the same slice method, we can also return an array using the same slice method. The syntax here will be the variable, which is the variable that stores the image, the row and column of the starting point. So it is row, column, then column, and then the row column of the ending point. So you know basically to draw a rectangle, you just need 2 points, then you can draw the 2 points. Let me demonstrate. If I have a point here and another point here, basically to draw the rectangle having these 2 points, we are just going to do something like this and something like this. So from 2 points, you can draw a rectangle. When we will look at image annotations, we will make better sense of it. So that's how slicing works. You just need a starting point and the ending point, and a rectangle is formed. So that rectangle contains particular pixels in between, and that is the array we are going to create out of the original array. To crop it, let's just visualize this as if it was some sort of matrix representation, and we wanted to slice a particular part. So what happens is, this part is going to be returned. So this basically is an array which is part of this general array, which is the old picture. That is what I mean by an array making an array out of an array. That's how you can look at slicing. If you look at this syntax being applied here, when we have this, we now store this new array into a different variable, and that variable can now be displayed using our matplotlib imshow method. If we that, we now have a particular portion of image. So here you see that everything aside the boat has been discarded. If we are to play along with this file, for example, if I wanted to have a wider view of this ocean, you can change this 200 to 50, then you print and you see that the image now has a larger view of the ocean. You see that the space between the boat and this line has increased. That's literally how you do it. And when you run it back, you see the distance has reduced because cropping from this part. When I initially put 0, it started from here to here. So it drew a rectangle. But when I put 200, it formed a square or rectangle around. So that's how we crop an image using the OpenCV library. There's no particular function. You just manipulate it the way you want using an array. So if you want to take a portion of an array and slice it, that's the same logic you will use when cropping the image. In this video, we will see how to flip an image. Flipping an image is changing the orientation of an image. There are two ways of flipping an image. You can either flip it along the y-axis or flip it along the x-axis. Or you can do both ways. Our OpenCV library gives us the flip method, which takes a source that is the input image and the flip code. Flip code is a flag which tells the flip method which particular flip operation to execute. So you can flip along the x-axis, y-axis, or both ways. These flags are almost like those of the imRead method. So there's 0, a positive value, for example 1, and a negative value, for example -1. When you pass 0 as an argument, it means you want to flip the image around the x-axis. Flipping the image around the x-axis means that the top will become the bottom and the bottom will become the top. If you pass in a positive value, let's say 1 or 2, it means you want to flip the image around the y-axis. Flipping the image around the y-axis means you want to flip it horizontally. That is, left will become the right, and the right becomes the left. And when you pass in a negative value, for example -1 or -2, it means you want to flip along both axes. So the top will become the bottom becomes the top, the left becomes right, and right becomes left. You run the code. We have 3 different images, each corresponding to each flag or flip code. The first here means that we are flipping it around the y-axis. The second means we are flipping around the x-axis. And the last we are flipping both ways. As we can see, we have 3 images here. But to be able to visualize better, let's see them one after the other. So I'll comment out these last 2 and these last 2, and if I run the code, now you see that we have passed in 1, and passing in 1 means that we want to flip it along the y-axis, which is equivalent to a horizontal flip. As you can see, this is the original image. This is the right, this is the left. And you see that this right here has become the left in the flipped image. And this was originally left, it has become right in the flipped image. So we have flipped it horizontally. Now let's comment this out and try the next flip. We have this, and when I run, we have 0. And 0 corresponds to a vertical flip. Why? Because we are flipping along the x-axis, which means in the original image, this was the bottom. In the flipped image, it becomes the top. And in the original image, this was the top, which becomes the bottom in the flipped image. Now let's see the last flip code, which is a negative value. And when you run, you see that the images are flipped both ways. So this was originally the right. It becomes left. This was originally the top. It becomes the bottom. So you see, this was bottom right. It becomes top left. When you pass a negative value here, it means you want to flip it both ways. And that's all about the flip method. So it's all about changing the orientation of an image. And if we comment everything back, and I decide to pass 2 here and -2, because it says any positive value or negative value, and when I run this, nothing changes. It is exactly as it was. That is about the flip method and basic image manipulation. See you in the next chapter, where we will see how we can perform image annotations. In this video, we are going to see how we can annotate an image. Annotate an image means you want to make a note, or you want to write, or you want to draw something on an image. And the various ways of annotating an image, we can draw lines, we can draw circles, we can draw rectangles, and we can add text. So we are going to see all of that. So the first thing that we need to do, as usual, is to make sure we import all libraries necessary. And here we just read. We are reading our image. And since the image is normally in RGB, and we are reading it using our OpenCV, we need to convert it, reverse it, so that when we are using our matplotlib to display the image, you maintain the normal color channel, which you can see. So run that. We have our image over here. And now the first annotation that we are going to see is drawing a line. So to draw a line, you virtually just need 2 points. You need the start and the end point. So between those 2 points now, the method for the computer is going to draw a line linking the 2 points that you mentioned. So to draw a line, the OpenCV library gives us the line method, which takes an image, the image on which we are going to draw the line. Then we have point 1, which is the first x, y coordinate. Since it is an image, it's a matrix. So a point is like a particular pixel, which has the x value and the y value. So it's going to be a tuple. Then we also have point 2, which is the second point of the line segment. Then we also have color, which is the color of the line you want to display or draw. So what it does is that we have point 1 and point 2. So you just draw a line linking the 2 points. Then the other optional arguments are the thickness, the width, or let's say the height of the line, how thick the line is going to be. And we have the line type, which of course is optional. And if you want to look at the line types, you can visit this link here. You're going to see all the various line types that we have. But usually we use this. This here is for the straight line that we all know. So here we're going to create a copy of the image that we already had, because this was the image over here. So we're going to create a copy of that image and store it inside a variable called ImageLine. And here we have our line method. ImageLine is an image. This image here, which we want to draw on. Then we have the first point, which is 200, 100. So it will be on row 200 and column 100. And the second point is going to be row 400 and column 100. So that means we're going to draw a straight line along the horizontal axis, along the x-axis. Then now we have the color. And remember, the color is in BGR, not RGB. It's going to be BGR since we are still within the OpenCV, but we are using an OpenCV method. Then we have a thickness to be 5. Then we have the line type to be this. And if we run this code, of course, you have to reverse it so that we can convert the BGR to RGB so that we can see it better. And we have this. So you see that this point here, we have 100, right? 100. And okay, this here is the Y, and we have 200 here. We have 100 and we have 200, which corresponds to this first point, right? And the second point, we have 400, which is this. Now we still have 100, which is this point. So I've just drawn a yellow line. So this here, this is BGR. This is a G, and this is an R. So R and red and green will give you a yellow. So if you were to manipulate this, for example, I'll take this to 300 and I run, you'll see that we'll not have a straight line again. We're going to have a line that is spinning. So that's how you draw a line very easily. So we move to the next annotation, which is a circle. Now to draw a circle, we just need a single point, which is the center. I will need the radius. From the radius now, we are going to start from the center, and from the center point, we are going to use the radius to extrapolate the circle around that center. So OpenCV gives us the circle method, which takes the image, which is the image on which we are going to draw. Then we have the center, which is the center of the circle. Then we have the radius, that is the distance between the center and the borders of the circle. Then we have the color. Then we also have our optional arguments, which are the thickness and the line type. So let's try this again. Here we created another copy of the image. I have installed it in the image circle. Then we now use our circle method where we have image circle, which is the image. Then we have 0.900. That's row 900 and column 500. Then we have a radius of 100, a color of red and a thickness of 5. So if we run this, we have something like this. So let's try to edit it. Let's try to take it somewhere around here. So I'm going to have, let's say, column. Let's say we want to take it somewhere here. So we're going to have something like this. We'll have row 400 and column 300. And if I run, we have it around here. Then the radius would just be how big or how large the circle is. Let's say we want to have a larger circle. Let's take 200 and run. Now I have a larger circle. So that was about the circle method, or how to draw a circle on an image. The next we are going to see is how we draw a rectangle. Drawing a rectangle is almost like drawing a line. But the difference here is that from the 2 points, we don't just link them. We don't just link them linearly. If we have a point here and we have a point here, we don't just draw a line between the two. When you have a point and you have a point, what happens is that we try to link them forming only straight lines, right? So if I have a point here and I have a point here, if I want to link this point, I cannot use a diagonal line. We try to link them using only straight lines. So if I have a point here and a point here, what we do is I will draw this first line. I'll do it this way. So I've linked this point and this point. Then we come again from here and do it like this. So at the end, we're going to have a closed shape which corresponds to our circle. Let's do this in practice again. So here you see that you have an image. You have point 1. You have another point. So you have 2 points. Of course, you have the color and the thickness. So let's go straight here. We have 500 and we have 100. So it corresponds to row 500 and column 100. Then the second point is going to be row 700 and column 600. So when you have this, I'm just coming this out. Okay, now we're displaying it without the circle. I just want to demonstrate something. So now I have row 500 which is this, somewhere here, and I have column 100. So this is the first point. Then I have row 700, which is somewhere here, and 600, which is somewhere here. So now we have these 2 points. We have a point here, and we have a point here. To draw a rectangle, what will happen is I'm going to do something like this. Then later on, do something like this, which is going to come out with the rectangle. So I'm trying to link the 2 points forming only vertical lines. So you cannot have a diagonal line. So you must do straight, 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 straight. So now let's uncomment this code and run it. We now see that we have that rectangle that was there. And if I try to shift this point backwards, we are going to have a rectangle of a bigger width. Same as if I try to shift it upwards. We are going to have a rectangle of higher height. The next annotation now we are going to see is how we can add a text. And how to add the text, we have 6 required arguments. The image, the text which you want to render. We have O, R, G, U, R, which is the bottom left corner of the text string. Right, so now we just need 1 point, which is going to be the bottom left corner of the text string in the image. Because to write a string, you virtually create something like a rectangle and the string will be inside. So at this point in time, we need just the bottom left corner, which is almost like 0.2 when we're creating our rectangle. So this bottom left corner corresponds to this place, this area here. And we have the font face, which is the font type, the font scale, which is the font size, and we have the color. And we run this, we have our written text here. So we have 200, 700, row 200, and column 700. You see that this is row 200, column 700. And excuse me, I made an error. It's bottom left, not bottom right. So it corresponds to the first point when drawing your rectangle. So instead of this, we have this. So this is the point that we need, this point here. So this is it. So that marks where the text is going to start from. And you can write whatever you want to write. So let's try to write something else. Let's try to write a welcome OpenCV tutorial. And run this, you will have it over here. And we have the font scale, which is like the font size. So if I increase it to maybe 3 and I run, you see that the scale or the size of the font has increased. And you have the font face. So to look at the font face, you have quotes. There are many of them. So you can visit the documentation and you're going to see all the font types or font families that you can use to write your text. So with that, this is all about annotating images. Annotating an image is basically trying to, for example, if you're trying to detect objects, right? When you have detected an object, you want to show the user where the objects are. So you need to annotate that image. So you can decide to show an object by drawing a circle around it. You can decide to show an object by writing a text on it. So that's what we mean by annotating an image. So it's like making notes or describing certain aspects of the image on the image. So with that, we can move on to the next chapter, in which we are going to see how we can work with videos and access our camera. Hello guys, and welcome to chapter 4 of our OpenCV tutorial. And in this chapter, we are going to be seeing how we can make use of our camera, web camera, or any visual device that is connected to your laptop or your machine. So we are going to be seeing how we can access it and see how we can read, write, and save videos. So the first thing that we are going to do, to be seeing right now, is how we can read videos. And to read videos, you first of all need the source, right? So the source here is the path to the video, and you need to remember, if you're going to use this notation, then that means that the video should be in the same folder with this code. So if I come here, you are going to see that this is the video and this is the code. So everything should be in one folder. Then you are going to create, I'm going to have a video capture, which we are going to store in the variable cap. So this video capture is what is going to allow us to be able to read or capture the frames in the video. So the first thing that you are going to do is to make sure all your inputs are there, then run this line. Okay, so now that you have kind of instantiated this video capture class, which is gotten from our CV tool, that is the OpenCV library, you want to check whether it is opened, right? So when it is opened, it means that we can go ahead and use that video capture object. And here we are going to use this method, which returns a Boolean true or false. False means that it is not opened. And if it is not opened, then we cannot use that object. So we come here, and if our object returns false when we call this opened method, then we are going to print an error that is a problem. That is, we cannot open the video stream in the file. Now, when we head over here, we have cap.read, open bracket, close bracket. So we have the read, open bracket, close bracket method, which is a method of the video capture class, and this method returns two variables. The first one is the read, open bracket, close bracket, which is a Boolean true or false, and this tells you whether the frame or the video has been successfully read. And this frame returns the actual image or the frame, because you know a video is made up of consecutive images, which is being played in real time. So this return here gives us true or false. That is, it tells us whether a frame has been read or not. And this frame here stores the actual frame itself. So if read, open bracket, close bracket is false, it means that no frame was returned. So this second variable frame here is going to store null. Then we can now decide to show it using our matplotlib. And remember, this is a syntax here to reverse the color, because we know that OpenCV works with DGR. But when you are using matplotlib while working with RGB, we have to reverse the channels. And when you do that, you have the first frame, which is returned. And this is it, which is displayed over here. The next thing now that we are going to do is learn how we can write a video. Writing a video is kind of like saving, like you want to produce a video and just save it. And so to write a video, you're going to use the video writer class. And this video writer class takes 4 parameters: the file name, a 4-character code, the frames per second, and the frame size. The file name is simply the name of the output video file, because writing is kind of like producing a new video. So when you produce a video, you have to obviously save it. So the file name is the name of the output video file. The 4-character code is a codec used to compress the frames. If you want to obtain more information about this, you can head over to Video Codecs by 4C page. And you're going to see a list of all the other 4-character codes that you can use to compress our frames. The next one that we're going to see is the frame rate. That is the number of frames per second. That is how smooth or how fast your video is going to look like. Because as I said, a video is made up of frames. A frame is like an image. So when you put these images, you just swipe over the images or play over the image in a seamless manner, it's going to appear as a video. So this frame per second now measures how fast the change between the frames is. They will also have a frame size that is the size of each video frame. So here, to get the width and the height, that is for these video frames, you're just going to get this. We're going to use the get method on our video writer. So we have cap.get3 and cap.get4. So we have this width and we have the height, and we transform them from float to integer. So you basically cut them. Now we're going to use our video writer, and this is the name of the file, which is race.car.out.avi. Then we have our first character code, which is this, and we have our frame rate, which is the number of frames per second. Then we have our frame size. A frame size is just a tuple, which is going to hold the width and the height. And we're also going to have another output video, which is going to be in MP4 format this time. And you see everything here is almost the same, except for the name, because here ends with .mp4, and the codec is going to be different. So as I said, if you want to know more about the various codecs that you can use, you can just simply come here to this video codecs by 4cc. So when you head over there, you're going to see more about the codecs and when you can use them. So when you run this, don't mind all of this. These are not actually errors. Just a warning telling me that some of my libraries might be outdated. So it's not a real pertinent issue. So when you run this, you're going to create a video. So if we come over to our previous folder, like our folder, you now see that we have this race car out.avi. And mine was already there because I had to rerun this code before coming here. But for you, you're going to see that these two files have been added. That is, the video has been written and has been stored in your folder. The next thing that we are going to see is how we can read the frames and write to a file. Read frames and write to a file. So what is it trying to mean here is that we're going to read a frame from a different video. So we're going to play a video and I'm going to capture each of the frames which we are now going to write in another video. So that's almost like duplicating a video. That's like copying and pasting or duplicating a video because you're essentially going to read a video. So while you're reading it, you're going to capture the frames of the video, and as you capture the frame, you write, you capture the next frame, you write. And that's how you read frames and write to a file. And to be able to do that, you're going to need to use a loop, because this time we are not just reading the first frame, we are reading the frames in a video. So we need to make sure that while the video is playing, we are constantly getting the frames, and as we are getting them, we are writing them. So when we look at the code here, you see that we have used our isOpened method, right? So while our video capture is open, we're going to perform this. We're going to have the read and the frame, which comes from our read method. And here we have if read is true, we now write the frame to the output files, else we break. So long as there is a frame, the variable read is going to be true. So while there is a frame, we are going to write that frame to a new output file. I'm going to do that so long as our video capture is open. And when there is no frame, you are going to break out of the loop. So when there is no frame, it's like telling us that, okay, I've come to the end of the video. So there is no frame again. So we loop, go out of the loop. So now we run this. And yeah, we can now have captured release. So this is like essentially it's to release. So it's like we're exciting, or we are telling the video capture that, okay, we are done using you. Then we also have the out AVI. This out AVI here was this. So we're writing. So we're going to need to release all of them. So we run. So we basically have this here. And if you're asking yourself where this out AVI and out MP4 are coming from, they are coming from here. Because remember, we're writing a video. We're writing a video to our file. So this is where they came from. So from here now, when we have written this video, we can now write frames onto that particular file that has been created. So that means that when we created this, if you went ahead and tried to play, you're going to notice the video was kind of empty. And now that we have essentially read the video from a different video, because if you notice this cap, this here was from the original video that we caught here. So we're basically reading this video and we are writing it onto that new video. So at the end of this, you're going to notice that the video now has something. It has some content. So I'll invite you to try it out when you do it. The next thing we will look at is how to access the camera. So far, we have seen how we can read and write videos, those videos which are already in the computer. Now we want to get a video real time. Say we want to perform some object detection or facial recognition. We need to be able to use the camera of the machine so that in real time, we can get the frames and images. And to do that, you need to first create a window. That is a window where you will have the video because it is real time. Now we will have video capture and we will pass in 0. 0 here means that we are using the main camera. That is the front camera of your machine. If you have a web camera or some other form of input device that can take in videos, you will specify different integers. And here we have while alive. So alive was created up here, true. And our window was accessing camera for these variables here. While it is true, we are going to read. We have source. We don't have cap anymore. The video capture class is now stored in this source variable. As we said, the read method returns a boolean, which is stored in this variable, and we have the frame. If the frame is correctly read, it will return the frame itself, and it will be stored in variable frame. Now if ret is false, that is, if there is no frame, we are going to break out of the loop. And if there is a frame, we are going to show it, and we will use the cv2.imShow method. We will use the window we just created here, and we will return the frame. If you run this code, you will notice that you will see yourself. It will be like you recording yourself and seeing the record live on the screen. We have created a window which will return the frame as it is being taken. So it will be like a real-time video record. The only difference is we are not writing to a file. You will just be able to see yourself. And when you press on the Q key, you're going to quit. So it is a command telling you that when the Q button is pressed, you will quit. It will be a live record, but you cannot save it. The moment you quit from the video, that is all. So for us to save it, we will use this. While it is true, we will write it onto a video file. So it can still be the same ones we used above. You can create a new one using a video writer class, or you can decide to use the same ones. Now at the end, you will play the video and you will see a record of what you did. But if you run this code the way it is, you will just have a record. So you will virtually see yourself in a small screen, which will have the name accessing_camera. If you run it, you will see the result. At the end of it, we are going to release. Release is telling the object that we are stopping and will no longer be using it. We are stopping the operation. The window which was created will be destroyed. That is all for camera manipulation using OpenCV. In this chapter, we are going to cover basic image enhancement using mathematical operations. We are going to see filtering. As usual, the first thing we will do is to import the necessary libraries. When we say basic image enhancement, we talk about arithmetic operations like addition, multiplication. We also talk about thresholding, and we also look at bitwise operations like the OR, AND, and XOR. The first thing we will be looking at is the arithmetic operations. That is the only operation we will be seeing in this chapter. In other chapters, we will look at thresholding and bitwise operations. We have this. Here we are basically reading an image and converting it, so we can have it in RGB format. When we have it, we have this. This is the image we will have. So the first question we will see is addition, and is also called brightness, because as we said, an image, like in this example, is a grayscale image. The grayscale image has just one color channel. It is a matrix with one color channel. And each pixel is a value from 0 to 255. So when a value is closer to 0, the darker it is. And when a value is closer to 255, the whiter it is. You see that when we add a certain number to the pixel number, it becomes brighter, whiter. So if the pixel value at a particular point was 2, and we added 5 to it, it becomes 7. So you see that the color becomes less dark. That is why addition is also known as increasing the brightness and vice versa. Because you know when you subtract, you're taking the image to a darker version. Because if a pixel value was 15 and you subtract 10 from it, you will have 5. And 5 is a darker number since it is closer to 0. So it is always addition, brightness, and subtraction, darkness. That's how we look at it. Now we are creating a new matrix. And this matrix is what we are going to be adding or subtracting, depending on the operation that we are currently doing. We have this np.ones method. This creates a matrix of ones. Now we will take the shape of the original image and pass it as the shape of the matrix that will be returned by this ones method. And the type will obviously be integer. So here we will be multiplying by 50. This multiplication by 50 means that it is going to multiply each value in this new matrix. So every value, which was 1, will be multiplied by 50. So we will have a matrix of 50s, and it will have the same shape as that of the image. We will print matrix, and when you run, you will have 50, 50, 50. That is because we multiplied by 50. But if I didn't multiply by 50, we will have a series of 1s. Now we have our matrix. We will now have a variable called ImageBrighter. We are going to add. What are we adding? We are adding the original image plus the new matrix. Remember, all images are represented in matrix format. When I pass this image here, it will not necessarily be this image, which will be passed. It is the matrix representation of this. And since this matrix was created using the shape of the image, we can add them because they are actually identical in terms of size. So when we add them, we will be expecting to see a brighter image. Because the pixel intensity will move closer to 255 because we are adding. And if we come down here, we are subtracting. The result here will be darker because when you take away 50 from the current pixel value, it will move closer to 0, which means it will be darker. And if you run this code, you can see it over here. Now you see that this is darker, and this is the original image. This image now becomes darker than this. If you were to access the pixel value here and here, you will see that here, let's assume that it was 155, which somehow a lighter shade of grey. If we take out 50 from 155, we are left with 105. And 105 gets closer to a darker shade of grey, resulting in this. So you will do this for each pixel. That's why it is very necessary that the shape of this matrix should be identical to the shape of this image. That's why we have to pass the shape as a parameter. This brighter is a result of addition. So you see that this was the original image. Here it was a darker grey, and when you come here, it is a lighter grey. That is because we have added 50 on the pixel value of this. Now when you do that for each pixel, you will have a lighter, brighter image. The next set will be multiplication. And multiplication is also known as contrast, because with multiplication, you are actually increasing the value. But it is different from addition, because the increase is uniform for every pixel. But with multiplication, it is not going to be uniform, because the greater the pixel value, the greater the increase. If, for example, the pixel value on row 0, column 0 was 2, and the pixel value on row 0, column 1 was 5, and we multiply by 10, you will notice that the first one, which was 2 multiplied by 10, will be 20. And the second one, which was 5 multiplied by 10, will be 50. So you see that the original difference was 30. But now that you have multiplied, the difference is 5. Whereas with addition, the difference between the intensities will remain the same because we are adding exactly the same value to each pixel. But with multiplication, the difference in color intensity will increase. So the difference between improving the contrast of an image and increasing the brightness of an image. So take note. Now look at this. We create two matrices by using our ones method, and we create the same shape of the matrix of the image. We will multiply by 0.8. You cannot use 50 again because it is going to give larger values. We use 0.8 and we are going to create a second matrix which is going to be multiplied by 1.2. And we have our darker and brighter. There is nothing like division. If you want to divide, you basically have to multiply by a number lower than 1. And when you want to multiply, you just multiply with a number above 1. That's no method called divide. You just have to use values below 1 and above 1. Now we have two images, the darker and the brighter. The darker one will be a result of multiplying it with this 0.8. And the brighter will be a result of multiplying our image with this second matrix. When we run it, we have this. You now see that the lower contrast, which is this, is darker because we multiplied it with 0.8. So 0.8 means we are actually reducing the values. So it's almost like division. When you reduce, the image becomes darker. And now when you increase the brightness, it means you are multiplying with a value above 1.2. But you must have noticed here that there are some areas that are kind of funny. This is because when you are multiplying, remember, color channels run from 0 to 255. So when you multiply, there is a high probability that you will have a pixel value which will be above 255. And when you have that, it will be a problem. Now, how do you solve that? By using the np.clip, that is, the clip method. And the clip method is accessed by using the numpy, which is np. So here, when we have this brighter image, we will clip it. So when we will multiply it with the second matrix, which is this matrix here, we are going to clip it. And clipping it means that we will give it boundaries. So we are going to specify 0 and 255. So you cannot be lower than 0 and you cannot be higher than 255. We have this. You might ask yourself why we don't also clip this one here. You don't necessarily need to clip it because it will never be less than 0. Because 0 star 0 will be 0 and 0 star by any number will remain 0. So you cannot be lower than 0. That's why we don't need to clip this image. Whereas with this, since it is 255, we can have a number above it. Let's say 200 star 255 is already above 255. So we have to bring it down to 255. And that's why we use this clip method. And using this clip method, we run, and you can see now the difference between these two. So no matter how the value we are multiplying by is, when it reaches 255, it will remain there. It cannot go more than that. So that's it about arithmetic operations. In this chapter, we are going to cover basic image enhancement using mathematical operations. We are going to see filtering. As usual, the first thing we will do is to import the necessary libraries. When we say basic image enhancement, we talk about arithmetic operations like addition, multiplication. We also talk about thresholding, and we also look at bitwise operations like the OR, AND, and XOR. The first thing we will be looking at is the arithmetic operations. That is the only operation we will be seeing in this chapter. In other chapters, we will look at thresholding and bitwise operations. We have this. Here we are basically reading an image and converting it, so we can have it in RGB format. When we have it, we have this. This is the image we will have. So the first question we will see is addition, and is also called brightness, because as we said, an image, like in this example, is a grayscale image. The grayscale image has just one color channel. It is a matrix with one color channel. And each pixel is a value from 0 to 255. So when a value is closer to 0, the darker it is. And when a value is closer to 255, the whiter it is. You see that when we add a certain number to the pixel number, it becomes brighter, whiter. So if the pixel value at a particular point was 2, and we added 5 to it, it becomes 7. So you see that the color becomes less dark. That is why addition is also known as increasing the brightness and vice versa. Because you know when you subtract, you're taking the image to a darker version. Because if a pixel value was 15 and you subtract 10 from it, you will have 5. And 5 is a darker number since it is closer to 0. So it is always addition, brightness, and subtraction, darkness. That's how we look at it. Now we are creating a new matrix. And this matrix is what we are going to be adding or subtracting, depending on the operation that we are currently doing. We have this np.ones method. This creates a matrix of ones. Now we will take the shape of the original image and pass it as the shape of the matrix that will be returned by this ones method. And the type will obviously be integer. So here, we will be multiplying by 50. This multiplication by 50 means that it is going to multiply each value in this new matrix. So every value, which was 1, will be multiplied by 50. So we will have a matrix of 50s, and it will have the same shape as that of the image. We will print matrix, and when you run, you will have 50, 50, 50. That is because we multiplied by 50. But if I didn't multiply by 50, we will have a series of 1s. Now we have our matrix. We will now have a variable called ImageBrighter. We are going to add. What are we adding? We are adding the original image plus the new matrix. Remember, all images are represented in matrix format. When I pass this image here, it will not necessarily be this image, which will be passed. It is the matrix representation of this. And since this matrix was created using the shape of the image, we can add them because they are actually identical in terms of size. So when we add them, we will be expecting to see a brighter image. Because the pixel intensity will move closer to 255 because we are adding. And if we come down here, we are subtracting. The result here will be darker because when you take away 50 from the current pixel value, it will move closer to 0, which means it will be darker. And if you run this code, you can see it over here. Now you see that this is darker, and this is the original image. This image now becomes darker than this. If you were to access the pixel value here and here, you will see that here, let's assume that it was 155, which somehow a lighter shade of grey. If we take out 50 from 155, we are left with 105. And 105 gets closer to a darker shade of grey, resulting in this. So you will do this for each pixel. That's why it is very necessary that the shape of this matrix should be identical to the shape of this image. That's why we have to pass the shape as a parameter. This brighter is a result of addition. So you see that this was the original image. Here it was a darker grey, and when you come here, it is a lighter grey. That is because we have added 50 on the pixel value of this. Now when you do that for each pixel, you will have a lighter, brighter image. The next set will be multiplication. And multiplication is also known as contrast. Because with multiplication, you are actually increasing the value. But it is different from addition, because the increase is uniform for every pixel. But with multiplication, it is not going to be uniform, because the greater the pixel value, the greater the increase. If, for example, the pixel value on row 0, column 0 was 2, and the pixel value on row 0, column 1 was 5, and we multiply by 10, you will notice that the first one, which was 2 multiplied by 10, will be 20. And the second one, which was 5 multiplied by 10, will be 50. So you see that the original difference was 30. But now that you have multiplied, the difference is 5. Whereas with addition, the difference between the intensities will remain the same because we are adding exactly the same value to each pixel. But with multiplication, the difference in color intensity will increase. So the difference between creating, improving the contrast of an image, and increasing the brightness of an image. So take note. Now look at this. We create two matrices by using our ones method, and we create the same shape of the matrix of the image. We will multiply by 0.8. You cannot use 50 again because it is going to give larger values. We use 0.8 and we are going to create a second matrix which is going to be multiplied by 1.2. and we have our darker and brighter. There is nothing like division. If you want to divide, you basically have to multiply by a number lower than 1. And when you want to multiply, you just multiply with a number above 1. That's no method called divide. You just have to use values below 1 and above 1. Now we have two images, the darker and the brighter. The darker one will be a result of multiplying it with this 0.8. And the brighter will be a result of multiplying our image with this second matrix. When we run it, we have this. You now see that the lower contrast, which is this, is darker because we multiplied it with 0.8. So 0.8 means we are actually reducing the values. So it's almost like division. When you reduce, the image becomes darker. And now when you increase the brightness, it means you are multiplying with a value above 1.2. But you must have noticed here that there are some areas that are kind of funny. This is because when you are multiplying, remember, color channels run from 0 to 255. So when you multiply, there is a high probability that you will have a pixel value which will be above 255. And when you have that, it will be a problem. Now, how do you solve that? By using the np.clip, that is, the clip method. And the clip method is accessed by using the numpy, which is np. So here, when we have this brighter image, we will clip it. So when we will multiply it with the second matrix, which is this matrix here, we are going to clip it. And clipping it means that we will give its boundaries. So we are going to specify 0 and 255. So you cannot be lower than 0 and you cannot be higher than 255. We have this. You might ask yourself why we don't also clip this one here. You don't necessarily need to clip it because it will never be less than 0. Because 0 star 0 will be 0 and 0 star by any number will remain 0. So you cannot be lower than 0. That's why we don't need to clip this image. Whereas with this, since it is 255, we can have a number above it. Let's say 200 star 255 is already above 255. So we have to bring it down to 255. And that's why we use this clip method. And using this clip method, we run, and you can see now the difference between these two. So no matter how the value we are multiplying by is, when it reaches 255, it will remain there. It cannot go more than that. So that's it about arithmetic operations. Hello guys. In this chapter, we are going to be looking at morphological operations, and morphological operations, we are talking about erosion, dilation, opening, and closing. So we are going to see that. The first operation that we are going to be looking at is erosion. From my normal understanding of erosion, what is erosion? Erosion is taking away the corners or the borders, right? So when you say the soil has eroded, it means that we are removing the outermost part of the soil. That's like the border. So when we are eroding an image, it means that we are trying to remove the borders around the image. So if you look at this image here, we have this letter G. So if we are going to erode this image, what it means is that these borders here are going to be scraped. And how is it actually done? It's done in a manner that's, a pixel. So a pixel is like a square in an image. So a pixel normally, right, has to be either 0 or 1. It has to be either 0 or 1, but now an image can be like this, and part of the image passes through the square. Let's take, for example, this square was a pixel, right? And we have a total image. So that an image can do this. So you see that this part here, let's say this part is white or blue. Let's just say white. And this other part here is black. So you see that this pixel here is like two ways. It's not totally covered by one color. So when you read there, you see a pixel in the original image. Either 1 or 0 will be considered 1 only if all the pixels under that kernel is 1. Otherwise, it is made to 0. Okay, pardon me for using pixel. Let's say a kernel. So this kernel here is made up of several pixels. And if this is a kernel and we have an image like this, we're going to make sure that all the pixels in that image should be 1. And if it is not 1, it will be taken down to 0. So it's kind of like an AND operation. And by doing that, you are cutting off the borders. Because if we had a kernel here, we had an image like this, what's going to happen is that this part here, this part of that image, that was like this, right? This part here is going to be cut off. Because this part here, the pixels under here are going to be 1, and the pixels under here are going to be 0, right? So in other words, this is a kernel. So everything here now is going to be taken down to 0. It's going to be taken down to 0, so in other words, we have eroded this part of the image. So I've cut it off. So now let's see that in action. So here we do this, and the result will now give you a thinner image. So you now see that if you look at this, and you look at this, you see that the borders have been eroded. So if you now look at this image, you see that all the kernels here are going to be uniform. The second operation we are going to look at is dilation. Dilation is the opposite of erosion. So the pixels under a kernel are going to be taken to 1 if any pixel is equal to 1. Remember, with erosion, we had a kernel. Let's just see this is our kernel here. Let's say the image is like this. So we have this part. This part of the kernel is 1, and this part of the kernel here is 0, and this part is 1. So what happens is, since there is a pixel that has a value of 1, all other pixels within this kernel is going to be rounded up to 1. So that now leads to dilation. So we're going to now have a thicker image. And if you look at it, this image is thicker than the original image, which was this. Then we have opening. Opening is another name for erosion, followed by dilation. So if you notice, erosion now is used in removing white spots from an image, while dilation is used in covering black spots in an image. You understand? Because white spots are like small areas that have a pixel value of 1. And what erosion does is that it will take a kernel. A kernel is like a small part of an image, which is made up of many pixels. So if the pixels within a kernel are mixed, there's 0 and 1, what will happen is that when we erode it within that kernel, if all the pixels within that kernel are not equal to 1, everything will be taken down to 0. So that's like we're now removing everything. We're now removing all the whites from the image. Let me take you over. If all the pixels within a kernel are not equal to 1, everything will be taken down to 0. So it's almost like an operation. 0 and 1 is equal to 0. So it's only 1, and 1 is equal to 1. So all the pixels within the kernel should be 1 for it to remain 1. That's erosion. So the white spots now are going to be taken out because they are going to be taken down to 0. Remember, 0 is dark, 1 is white. Remember? Then now we have dilation. Dilation means that if at least one pixel within a kernel is equal to 0, everything within that kernel will be taken to 0. So that's the difference between erosion and dilation. So now if we have, if at least one pixel within a kernel is equal to 1, everything within that kernel is going to be rounded up to 1. So you see, you can have a white image and you have a small dark spot there. What will happen is that we're going to create a kernel. And since at least one value there is equal to 1, everything is going to be 1. So even the values that were 0 are going to be taken to 1. So that's why we call it dilation, because we are removing black spots. Erosion removes white spots and dilation removes black spots. So we'll talk about opening. We'll talk about erosion followed by dilation. And when to do that, you have this method here. Very explicit. And this one takes in an image, this flag, and a kernel, right? So the kernel here was this. So the kernel now, so every pixel within that kernel, that's what we're testing. So we have this and we have this. So you notice now that all the white spots have been removed. Then the black spots now have been removed. So it's like removing the noise in an image. So if you look at this image here, you had this white spots which were removed by erosion. Then now the remaining black spots that were within the white images were closed, which was as an effect of dilation. So that we'll call morphological opening. Now we have morphological closing, which is in reverse. So we dilate before we erode. So this is now useful in closing small holes inside foreground objects. So now we have black spots in between this. This all happens now is that we dilate, then we erode. So now why do you have to dilate and erode? You notice that when we have, for example, this is the actual size of the letter. When we dilate, what happens? The image becomes bigger, right? The image becomes bigger. Like if you take a look here, the image was bigger than the original image. But that's not what we want to have. We want to remove these black spots without an increase in size of the letter. So what happens now is that when you dilate, these black spots are removed and this J, this letter here, became bigger. So we had to erode after that so that it will be brought back to its original size. Because remember, erosion shrinks the image. Dilation broadens the image. So after doing this letter here became bigger and we had to erode it to bring it back to the original size. That's the very concept we're opening. When you perform erosion on an image, it shrinks. So now here, we just wanted to remove the white spots by shrinking these white spots. That is, when you shrink such a small value, it becomes 0. I want this to be 0. It will remain 0. So after doing that, this letter J is going to become smaller. The matter that we dilated to bring it back to its original size. So that's the logic behind opening and closing. So that is it for morphological operations. There are some more which you can always look at in your own time. So remember, this is just a tutorial to guide you, to introduce you into the OpenCV library. So always welcome research. There are many things that you can now look at on your own and add to what is in this video. So without further ado, we're going to move on to the next chapter. Welcome to another chapter in our OpenCV tutorial. In this chapter, we are going to talk about image thresholding. And this is one of the most important concepts in computer vision using OpenCV. Or it is a very important concept in general. What is image thresholding? This is a very fundamental technique in image processing used to simplify and segment images. It converts grayscale images or color images into a binary image. Binary image means it is made up of only two pixel values. Either it is 0 or it is 1. Either it is 0 or it is 255. There are only two possible pixel values. It takes a grayscale or a color image and transforms it into a binary image, where each pixel is classified as either belonging to the foreground or background. When you have an image, since it converts it into a binary image, that means there will be only two visible things on the image. Either the background might correspond to 0, which is pure black, or a foreground, which might correspond to 255. The process of thresholding involves setting a threshold value. That's where it gets its name. A threshold value is simply a value below which you will do something, and if it is above, it will do something. For example, if I have a threshold value of 200, or let's say 100, when trying to perform threshold on an image, for every pixel that is below 100, it will be converted to 0, and for every pixel above 100, it will be converted to 255. That's how image thresholding works. The main objective of image thresholding is to simplify the image and extract meaningful information by emphasizing regions of interest or separating objects from the background. And it is used in various image processing applications, such as object protection, segmentation, edge retention, and feature extraction. It is a very fundamental concept because we will have to perform thresholding when we want to perform bigger tasks. So there are different types of thresholding techniques which we are going to see. So OpenCV provides us with a method which we can see here. So this method takes a source which is the source of the image. It takes the value, the threshold value, the value that we are going to use as a check. Then it takes the maximum value and the type of thresholding we want to perform. So let's look down. So if we come here and we run this cell, so here we are importing all the necessary libraries that we are going to use. And here I have my image, which is this piano sheet music PNG. And I'm going to convert. I'm going to read it in a grayscale format. Right. So I'm going to use a grayscale image. Then over here we have our threshold function. So the threshold function returns two parameters. One is the image. That is the image after thresholding has been done. And we also have this variable here, which will store the type of thresholding we performed. So there are actually several types of thresholding, but the most popular, we have the binary. As you can see here, which is denoted by cv2.thresh underscore binary. So what this does is that the pixel value in the image is compared to a fixed threshold value. In our case, our threshold value is 100. If the pixel value is greater than the threshold, it is set to a maximum value, which is this. So if any pixel is greater than 100, we are going to set. We are going to change that pixel value to 255. So it will be pure white. And if it is below 100, it's going to be converted to 0, which is pure black. So that's how binary thresholding works. We also have inverse binary. Inverse binary is quite the opposite. So if it is above 100, we are going to convert it to 0. And if it is below 100, we are going to convert it to 255. So this is usually used when we want to get the background. Once we get the background of an image and throw away the foreground. But with binary, we want to get the foreground and throw away the background. So let's see how this works. So when I run this, okay, so this is the original image here. And you can see that every pixel that was above 100 was converted to white. So here we have a binary image. So either it is black or it is white, right? And here you can see that we are trying to get the foreground. Foreground is like an object or an image, while the background is simply what is behind the object. So you can see that this grey is kind of like a background. And the actual foreground here is all these writings, what you are actually looking at in the image. So you can see that here we are actually making more visible the foreground of the image. And you can see that this whole part here is kind of black because you can see that the lighting conditions in the image were not equal. So when you approach this sector here, you notice that it is somehow darker. And obviously it was below 100. That's why it was converted to 0 and resulting to this black section of the image. So if I come here and I add inverse, what happens? Let's run our cell. Okay. Now you see that it has been inverted. So what was originally black became white, and so that was the concept. We also have other ones. We have trash to 0. Let's see what it does. Sorry, there's no binary there. Okay, so you see that this is another vibration. And if we take inverse of this, you see, so whenever you add inverse, it's always more like just getting the inverse of what you originally did. So what was white will always become black, and what was black will always become white. So after that, another set or another category of thrash to 0 is what we call the adaptive thresholding, which you can see here. So with adaptive thresholding, the algorithm determines the threshold for a pixel based on a small region around it. So we get different thresholds for different regions of the same image, which gives better results for images with varying illumination. So you notice here that in this image, the lighting conditions are not actually the same. The lighting conditions were not the same. So let me take this back to binary and rerun. Okay, seeing the lighting conditions were not the same. That's what resulted in this very dark place here. So this is not a nice situation because there is actually content here. There is actually some of this piano writing here, but over here, everything is black. That's because the lighting conditions were not the same. So what adaptive thresholding will do now is that each region will have a different thresholded value. So it will be adaptive, it will be adaptable. So it will adapt itself to the illumination of a small region around the pixel and calculate its threshold from that. So over here, the threshold value will be calculated from a certain region around it. So from a certain region around it, we can now get the threshold value for a specific pixel within this area. The same thing goes here. So the threshold here will be different from the threshold here, because if you look at the surrounding area over here, you notice that it is somehow darker. So the threshold value here will be lower. And over here, which is somehow lighter, the threshold value will be higher. And how there are methods. There are different methods in which the threshold can be calculated. We have the main adaptive. So the threshold value for each pixel is calculated based on the main intensity of its local neighborhood. So you just take the pixel intensities of all the areas in a particular region and calculate the mean. So from the mean intensity, we now get the threshold value for a pixel within that region. Another method is the Gaussian adaptive. So it computes the threshold for each pixel based on a weighted sum of intensity in its local neighborhood. So this one is a little bit more complicated because it involves weights. When we talk about weights, we can always explain weights more when talking about quadratic equations. So if we have, let's say, a plus b equals x, right? I have another equation where you have a plus 2b equals x. You notice that the weight of a is 1 and the weight of b is 2. So I'm trying to tell you that b is a more important variable to a. So b is more important than a because you have an equation a plus b equals x. I have a plus 2b equals x. So I'm trying to tell you that b is more important than a in finding x. So that's how you can look at weights. But now our OpenCV gives us another method, which is now adaptive thresholding. And with adaptive thresholding, it takes the source, it takes the max value, it takes the method, that is the adaptive method, which can be the mean adaptive or the Gaussian adaptive. It takes the thresholding type, the block size, which is the size of the pixel neighborhood, which is used to calculate the threshold value. Because it will take an average from a certain portion of the image and will do it. So ideally, you don't want the portion to be too big. If not, it will not actually give you an accurate threshold value. You want it to be somehow small or the appropriate size actually. So you need to be very careful when considering the block size. If it's too small, you will not give enough information. And if it's too big, there will be too much information. And in the end, the threshold value will not be accurate. So let's see this in concept. So I'm going to see it over here. We have, let's say you want to read this image, right? So what we're going to do is that I'm going to try to perform thresholding on that image using different techniques. I'm going to see and compare which one is better. So I'll just comment this here and this. So when we run this, this was our original. It's almost like this. Okay. The thresholding value was different. So our threshold here was 15. As you can see, our threshold here was 15. So what happens if I increase the threshold value? We have something like this. I used to see that when you increase it. When you increase the threshold value, the dark places will become bigger, right? And if I reduce this, let's say to 15, then the dark place will disappear. But now the writings will also disappear. So you see that with normal binary operations or with normal threshold, it will be quite difficult to get an appropriate value, which will make all the writings visible. So if I comment this, and now let's try to use adaptive thresholding. I'm going to see how it looks like. So comment this, and now comment this. Okay. Now you can see that the writings are very, very visible. Why? Because it adapts itself to the illumination of a particular area. So when it came over here, you notice that the portion around here, which the pixel is located, was somehow dark. So what happens was that it reduced the threshold value for that specific area. So the threshold value for a pixel within this area will be different from the threshold value for a pixel within this area. So that's what results in this very, very well adjusted and thresholded image. So if we now decide to display all, we can compare. Okay, now we see that this is the best. So adaptive thresholding is always the best method that you're going to use when you're going to be thresholding. So now, depending on the particular use case that we want to perform, you can now decide to change the adaptive method. Let's say we're using the threshold mean C, and there are other ones. So you can just test, test, and test. And you can come up with the one that suits you better or produces the best results for you. The next thing that we are going to see is contours. What are contours? Contours are simply curves joining all continuous points having the same color intensity in an image. And contours are a useful tool for shape analysis, object detection, and recognition. What does it mean by joining points having the same color intensity or intensity? It just simply is trying to tell that it is used in finding the borders of an object in an image or all objects in an image. Why do I say borders? Borders are actually lines if you look at it very well. Borders are actually lines of the same color or the same intensity. For example, when we use our canny edge detection method, where everything became pitch black, and you saw the corners of your face or the corners of the object becoming white, those are the same color intensity, and the same color intensity will always match the borders. They already tell that it is used for object detection. Object detection can also be seen as feature detection. And in our canny edge detection, you notice that we were actually trying to detect the edges. Edges are almost like borders. So from the borders, you can now know that this is a particular object. So that's what contours are all about. And for better accuracy, we usually use binary images. We use binary images because if you're using a color image, it will be very hard to get points of the same color intensity all through. It will be very, very difficult because color images are so many colors. They might be alike, but there might be slight differences in the pixel value, and it will result in lower accuracy. So whereas when you have a binary image, point to either this or that. So there are only two alternatives. It's either 0 or 1 or 0 or 255. And that will make it easier for our contour detection method to identify areas with the same color intensity. So how do we proceed? Coming here, the first thing is that we need to have our binary page. And as we saw in the previous video, to get a binary image, you need to perform thresholding on that image. So here, perform thresholding as a first step. Actually, the first step will be to get your image and convert it to a grayscale image. We usually use grayscale because grayscale will always provide better results because there are less colors to deal with. So after converting it to grayscale, now perform thresholding. And we now use the method which OpenCV gives us, which is find contours. So this find contours method just simply returns all the contours or all the continuous curves of the same color intensity. So from when you get those contours, you can now draw those contours on an image. And you'll be able to get maybe edges, you'll be able to get borders and everything. So the first step here will be to find your contours. And this method here, this method takes 3 arguments. The first is the source argument, or the source image. The second is the contour retrieval mode. And the third is the contour approximation mode. So for the retrieval mode and the approximation method, you can always research that on your own. But for this one, we are going to use retrieval 3. That is, without 2. We are going to use a simple approximation method. And here, I've just printed the contour. So it actually gives us 2 variables, 2 results. One is the contours, and the other one is the hierarchy. Hierarchy here is simply the precision of the contours. We're going to see that below. So when we run this, we have here, I have my array of contours, which corresponds to the points in the image that we can use as contours. And this second one here is the hierarchy. So after getting the contours, the next step is to draw them. So our image that we took from there was a rectangle. So from here, I can draw, and that's it. So here we have draw contours. So a rectangle has how many? Like the borders of a rectangle would be. It would be obvious. It would be quite obvious. As you can see here, I've colored them green. So this is it. So you can see what's colored green here. This is the contours. And you can also see that it corresponds to the borders of a rectangle. Why? Because the rectangle was drawn, right? The rectangle is drawn as the way you draw it. So we want to link curves of the same color intensity. You'll notice that it will be the very borders which are going to be written, because the borders are drawn with the same color, the same intensity. Yes. So you can see the side to change the color right here. So you can see that this is, let me take a blue. Blue is more visible. So you can see that this is it here. So don't bother about this dark image. The dark image here is that because there is no particular curve inside here. Everything is just black. So you cannot just color everything blue because this is not a curve. When we mean curves, we look at lines. Looks for lines with the same color intensity. Right. So over here, this is not actually, there are no lines here. It's just a whole black place, a whole black part of the image. So that's why here it's not colored blue. It looks for lines. Right. And here you can decide to get the exact contour. Like you don't want to draw, or you want to draw only a specific contour. Let's say this 0 here will correspond to maybe the first contour of the image. And that's it. Then now we look at the contour approximation method. So with the approximation method, we have 2 lines. We can have this chain approximation symbol. We have this chain approximation symbol, and we have chain approximation node. With chain approximation node, all the boundary points are stored. But now the question is, we don't actually need all the points. We just need specific important points, because from these important points, we can actually draw the remaining part of the contour. And that's what chain approximation symbol will do. It removes redundant points and compresses the contour, thereby saving the memory. So yeah, you see that if we were to use approximation symbol, we are going to have all the contours. And you can see that this matrix that is written will be bigger. And when it is bigger, it takes more memory. But with approximation symbol, you take only specific important points. So redundant points are going to be discarded. So you will give us a smaller matrix, a smaller array which contains the method, and it will thereby save us more space. Now if we look here, we see that the first image, which is this, used approx node. So it gave us all the points of the contour. So you see, this is the color blue. But now when we use a proc symbol on this very rectangle, we had just 4 points. I noticed that from these 4 points, we can still be able to draw the border or draw the edge of this image. So bear in mind that this image here is quite different from this image, because this image is a simple rectangle and this was a different kind of image. It was like a rectangle divided into two, which one was a different color. The other one was a different color. That's why it had to draw it all around, even though we used the approx symbol, which we have a method. So bear in mind that these two are not the same image. If you had an image that was in this format, you'll notice the difference. So with the approximation node, it returns 734 points, which will correspond to all the points here, which are colored blue. So it is continuous. But actually, we will not actually need all of this. That's why approximation symbol is now used, which will return only 4 points, which are this, this, and this. And if you have these 4 points, you can easily draw the border of this rectangle. You can draw the edges of this rectangle. So you'll notice that with these 4 points, we can still do the very thing that we can do with all the 734 points. So that would be it for image thresholding and contours. Hello guys. In this chapter, we are going to be seeing image alignment. Imagine you have two images of the same scene captured from different perspective to angles. Before we can analyze or compare these images effectively, we need to ensure they are perfectly aligned. That is where image alignment comes from. So you can now look at these two images here. They were actually the same documents, but they were captured from different angles. So our aim now will be to convert this to this. So we are just simply trying to align it. I'm going to align it using another image. So we need an image which has the proper alignment and the image which has the bad alignment. So we'll use the image that has the proper one to align the other image. So image alignment involves adjusting the position, the rotation, and the scale of one image relative to another, so they match as closely as possible. And this process is essential for tasks such as panorama image stitching, object recognition, and image illustration. So that just goes to explain what I was saying. So you actually need two images because you are aligning one image relative to the other. So you obviously need an image that is already properly aligned and use it to rotate or adjust the perspective of that other image so that you match the other image as closely as possible. So here we have this image and we have this image. Notice that this one has a proper adjustment, not so straight, but at least this is better. And this one is actually rotated in a funny way. So we might want to align this using this. So that's what image alignment is all about. And a powerful tool for image alignment is homography. Homography represents a transformation that maps points from one image to corresponding points in another image. So what happens is that we have first of all identify the points that are similar to. So we have this yellow point, this green point, and this red and orange. I also have the very points in this image. So homography will now present a transformation which is somehow like a matrix, which we can apply to this image, and it will transform these points here to these points. So it's almost like with normal matrix transformation, when you want to rotate an image, you apply a certain matrix and certain 2 by 2 matrix to that image. And the resulting matrix would be that very image, but rotated a certain degree. That is the very concept that we are trying to apply. So that matrix, that transformation matrix, is going to be called homography. So when you apply the homography matrix to this point here, let's say this is a shape right here, this matrix here, because this will be a shape which is told by a matrix. So that matrix will be transformed into this matrix, thereby aligning them. So in order to do that, we're going to start by importing all our necessary libraries. We just need our OpenCV, NumPy, and matplotlib to display everything. So the first step here is that we are going to read the template, and we're also going to read the scanned image. So this is not the example that we're going to be using. We are going to be using this form. I'm going to be using this form as an example. So let's go to the first one. It's the reference file name, and the second one will be the image to be aligned. Take note when you hear relative, it means that we're going to use two images. So we read them using our inRead method, and we convert them to algebra, because we're going to be using matplotlib to display the images. So when we run the cell, it displays images. So these are images that we want to align. So this is the original form, and this is the scanned form. So you notice that this is not really properly aligned, and this is really not an application of it, because this is a document that was sent to you, right? And you printed the document, and you have written and filled all the information that was necessary. And you didn't have time to go to a photocopy machine or something to scan it. You just used your phone. You used like a little scanning app on your phone to scan it, and the adjustment was not that good. The adjustment was not that good, but you're not going to send this to maybe your employer, of course. So now you want to get this to look like this, but with the information where you have filled right. So that's kind of what we want to do in this small project or small exercise. So step 2 will be to find key points in both images, So key points are like corner points. Key points are corner points, and these points are very important because we are finding 4 key points in both images. So the key points or the corner points should be found in the 2 images. We need to find the key points that are in the 2 images. So what will happen is that we will start by finding the key points in this image. I will find the key points in this image. Then after that, we are going to try to map the key points in this image to this image. So we are going to now get like an intersection. We're going to get the points that are similar to both images. And those are the points that we are going to be focusing on. So the thing is now we're going to convert both images to grayscale images. As I said, grayscale images always allows a better precision. And here we are going to compute features. So when we are doing feature detection, we looked at good features to track. But there are other methods. As I said, there were other methods, and one which they are going to see here is the op_create method. And there is also the shift. There are many of them. But as I always emphasize, if you are to look at every method in the OpenCV library, we are going to have a tutorial of 3 to 4 days. So majority of the work you need to look at in the documentation of OpenCV. In this step, we are going to be computing the features. Those features also can be called descriptors because those features are kind of going to describe the image. So we want to get a max number of features, which is 500. So we're going to create this. So this is like the class. So we're creating an object of that class with maximum number of features to be 500. From there now, we are going to get the key points and descriptors for each image. So key points 1 and descriptors 1 is going to store the key points and descriptors of the first image, which is the reference, and key points 2 and descriptors will store the second image, which is the scanned image or the image that we want to align. So we are going to detect and compute the features and the descriptors. So after having done that, the next thing that we are going to do is draw them. So we'll draw these key points 1 and descriptors 1 on the first image, which is the reference image. I'm going to draw key points 2 and descriptors 2 on the second image, which is the scanned image. Then, when we do that, you can now draw them and you can see all the descriptors, all the corner points of both images. They are circled red. So you can see them. There are 500 of them. So that's why there are many, and they are so saturated in some particular areas, specific areas that have drawings and writings. So the next thing that we have to do is that you notice that not all the points here are found, because here actually has some writings, because the person has filled the form, and those writings also have corner points. That's why you see there are many corner points around here. You see that over here, they are not there. But since we are trying to use an image to align the order, we need to match the key points. So we are going to look for the points, the corner points that are here, and also in this other image. So that leads us to step 3, which will be to match the key points in both images. And to match the key points in both images, we are going to use the descriptor matcher create class. And this descriptor class here takes one parameter, which is the method. So this brute force Hamming indicates that we are going to use brute force method for matching descriptors based on the Hamming distance. So this is the method that we are going to be using to match the key points. Obviously, there are going to be other methods which we can always look at in the documentation. So after creating this, instantiating our object from the descriptor class, we can now use that class to match the descriptors of both images. So we'll take the descriptors of the first image and we'll try to match them to the descriptors of the second image. Then when we do that, the next thing that we want to do is to sort them. So we are going to sort them based on their distance scores. And we're going to sort the matches in ascending order of distance. Because as we said, this matcher here matches them using the hammer distance. Using the hammer distance, we are going to have many points of different distances. So now the issue here is that we now need to sort them according to distance, because the ones with the furthest distance are going to be less important, and the ones with the closest distance are going to be more important. Obviously, so we are going to sort them in ascending order. Then having done that, we are now going to remove the matches which are not important, and I'm going to remove the matches that are not so important. So we are going to take 10% of the matches that were returned, 10% of the matches. So that's just 10 divided by 100, which is 0.1. So we multiply that by the length of the matches, the length of the number of matches that we return. So that's 10%. And now we are going to string. We are going to slice that number. So if 10% of 500, because we specified 500 people, say 10% of 500 is going to give us 50. So now we have 50 matches. Now we have these matches. These are the matches between the two images. So now what happens is that we want to draw those matches, and to draw them, we are going to pass in the image. That is the reference image, and its key point, and the scanned image, and its key point. That's why we have image 1 and key points 1, image 2, and key points 2. So we do that using the method called draw matches. So having done that, we now display our result. You are going to see the way the two key points are being matched on two images. So we had no 1 this cell. So now we run the cell and we have our result. So now we have tried to match the key points that are similar to both images. And those matches are going to be stored in this variable here. So the next thing I want to do is find the homography. So we want to get the matrix, which we are going to apply to this image in order to rotate, scale, or translate if necessary. This image to look like this image. But to find the homography, you first of all start by creating a matrix with zeros, and it should match the size of our matches. That's what we get this. So this year, I just learned matches 2, which will indicate that it has this number of rows. It will be this number of rows, and we'll have 2 columns. We're going to create 2 different matrices, which will be filled with zeros. Okay, so we have a loop. The loop iterates over each match in the matches list, which is the right. So this loop will iterate through each match in the matches list. And for each match, it retrieves the index of the query point, which is this. We will try the index of the query point and the index of the train key point, which will be this. So let me take it over. The loop iterates over each match in the matches list. For each match, it retrieves the index of the query point and the index of the train key point. Then it uses these indices to access the corresponding key points, which is now this year. So when we get the query index, we now use it to access the point of the corresponding key point. And after that, it stores them in points 1 and points 2 variables. So key points 1 corresponds to the first image, and key points 2 corresponds to the second image. Then we are going to use the find homography function to estimate the homography matrix. This function takes 2 sets of corresponding points, points 2 and point 1 representing key points in the destination and source images respectively. So notice that we have reversed it. So it's going to be point 2, which is the destination image. The destination image is the image that we want to align or apply the homography on. So the last argument of define homography function will be this ransack, this over here. So this ransack specifies the method used for finding the homography ransack, means random simple consensus, which is a robust estimation method that iteratively fits the homography model to a subset of correspondences while discarding outliners. So we don't really need to know how it does it. We just use it by that abstraction. So this CV2 ransack is one of the best methods to find our homography, and that's why we are using it. So this homography now returns 2 values. H is H here, which is the estimated homography matrix, and the mask here is a binary mask, indicating which matches were considered. And that's which matches were considered inliners and which matches were considered outliers by the algorithm. That is the ransack algorithm which we use. So when we get that, what we want to do is that we want to apply that homography matrix to our scanned image. So as I pointed out earlier, it's almost like matrix transformation. When you want to rotate a matrix, you are going to use a smaller matrix. It can be 2 by 2 matrix, which usually vary. They are fixed. They are actually fixed. I cannot really remember, but let's say you want to rotate a matrix 90 degrees. You're going to apply a certain 2 by 2 matrix to the matrix that you want to rotate. So when you apply that matrix to the matrix you want to rotate, is going to the result matrix will be that matrix rotated to a particular angle. That's almost the very thing that we're going to use with our homography. Because to get this image to this image, you have to rotate it to a certain angle and scale it to a certain point to create to a certain extent. And you might also need to translate it. So all of that information is going to be stored within the homography. So that homography matrix will be able to rotate, scale, and translate if necessary. So in order To do this, how do we apply the homography matrix to the scan form? We're going to use the warp perspective method. The warp perspective method, and before doing that, we need to get the height, the width, and the channels of the first image. It's very important. We need to get the height, width, and channel of the first image. Then now in our warp perspective, we're going to pass in the second image, which is a scanned image, the homography. And now we are going to pass in the dimension, that is the width and the height, and it has to correspond to the width and the height of the original form or the reference image. Having done that, we can now run, and let's say H is not defined. So I do not want this cell. And let's run it now. And you can see that this image has been aligned. And you now see that both of them are aligned the same way. So since this is aligned with reference to this, it will always look something like this, where this image was upside down or not properly aligned. You're also going to have the very same kind of result here. So this image was upside down. This image to be upside down. This image was slanted 45 degrees. This image to be slanted 45 degrees. What does that tell you? It tells you that your reference image should be as close to the result which you want to obtain as possible. So if you take a bad image as a reference, you're going to have a bad result. So that is it about image alignment. In this video, we will see how to create panoramas. To be able to create a panorama, we should be able to stitch various images into one image in such a way that the result will be an elongated image. To be able to create a panorama, we need to find all the key points in all the images, then find pairwise correspondences. So, we need to find the key points that match in the images. After that, we estimate pairwise homographs. We refine them, then we stitch them with blending. Essentially, what is being done from step 1 to step 4 is basically a form of image alignment. Because stitching an image is like merging images together. So if I want to take a picture of, let's say, a white landscape, it will be very difficult because unless you zoom out, it will be very difficult to take a wide picture. What you do is that you can take a normal picture, you shift your camera to the left, you take another picture, you shift your camera again to the left, and take another picture. After that, you can now shift to the right and take another picture. At the end, you will have 5 images which you will stitch. At the end of the day, it will be like you took one picture or one capture of the whole wide image. To be able to stitch or merge pictures, they need to be perfectly aligned. We are going to use one image as reference. The image is usually the one found in the middle. We are going to align the other images such that when you merge them, it should be seamless, like it was one picture. After we have done all the necessary alignment, you can now stitch with blending. The first thing we will do is to import our libraries. The only additional library here is the globe library. Here, we will use our Stitcher class. We read the images using this globe library that we have here, and we use the globe method where we are going to access. So all the images are inside this boat folder, as you can see here. This boat folder has all of our images. We are going to read them and sort them. After doing that, we are going to read each of those images and convert them to RGB. Having converted them, we will add them to the image list we created above here. We will now store the number of images present in that list. Over here, we just display the images. So these are the images that we have over here. These are six different images that were taken of the same place, but since the object we wanted to capture was so wide, it could not be taken in one snapshot. We had to perform 6 snapshots to be able to capture the whole object. Now these 6 snapshots are different, and having these images, you cannot really have a view of what we tried to take. What happens is we need to stitch or merge the images together. So at the end of the day, we will have one image which will depict the object clearly. Now we move here, we will use our stitcher_create class. We will expedite it, and here we have our object stitcher. Now we will use the method stitch, which takes the images. These images are a list of images we want to merge. These images here correspond to this image list here, which we later added all our images in the boat folder to. So these images here are stored in this image list, and this is what we are going to pass this over here. When we do that, we make sure the status is 0. Status equals 0 means that it has successfully stitched our images, and now we have this result. We now have a clearer view of the object we were trying to take. This is kind of a view from this end to this end. But with this bigger picture here, you will not really have a bigger picture of what we were trying to take. But when we stitch them, we now see what we are looking at. And you cannot take this kind of wide picture using just one snapshot. It is almost impossible. That's why in your camera, there is a particular setting called Panorama, where you basically move your camera to the left so you can capture a wide picture or object. If what you are trying to take a picture of is too wide, you can now switch to the panoramic view, where you basically start from one end and move your camera to the other end. What happens is, as you are doing all of that, it is taking different snapshots, which at the end will perform alignment and stitch them. And at the end of the day, you will have one image. Welcome to the last chapter of our OpenCV computer vision tutorial. In this chapter, we will look at a project, and a very interesting one, I will say. The project is all about object detection. In this project, we will see how we can detect objects in an image and say with a certain amount of confidence which object it is. So, to walk through with this project, you must use a model. We need to use some kind of classification model. A model that identifies an image as what it is. And the object is now going to be imported and used within our project to be able to get the objects in the image we are going to provide. Building a model is out of the scope of this tutorial. So we are going to import an already made model from the TensorFlow Model Zoo. This is an area where there are some already made or pre-trained models. We just need to pick the model we want, and we import it. This project is going to be organized in some steps. The first thing we will do is to load the pre-trained model. It is a deep learning model, and since it is not part of the scope, we are not going to get into how the model was made. We are just going to import it, load, and use it. OpenCV also gives us methods to be able to download or load TensorFlow deep learning models. The next thing we will do is to read the image and do any pre-processing on the image if necessary. Then we pass the image into the model, and the model will give us the objects that are there, and we will now display it on the image so the user can see the object and the label. In the next video, we will get started with the project. Okay, so now we are going to dive straight into writing the code that is going to make us be able to detect objects in an image. So the first thing that we are going to do is download the model. And this is a pre-trained model. So it has been tested and it has been proven to be accurate enough for us to be able to use it. And it's quite free. So if you want to look at where you're downloading the project from, or the model, sorry, you can visit this link and you'll be redirected to the GitHub repo, where you're going to see the model. So the first cell here, we are just going to import everything that we are going to use. So we have OS, that enables us to manipulate the operating system. We have CV tool, which is our OpenCV library. We have NumPy. We have URL lib. So this is simply a library that enables us to download documents for the model from a particular URL. Then we have matplotlib, which we already know. So now we are going to create a config file from a frozen graph. So the first thing we are going to do is to extract the files and everything. So this model file here, this is like the path. This is the path to the file. So if you move here, you're going to see that this is models and we have it here. So we are specifying the path and we also have the config file and we specify the path as well. Then we also have the class file. So all of them are already here. And I think the class file should be out of it. Okay, yeah, this is it. The next thing we're going to do is, okay, now if you're going to download the project files directly from the link that I'm going to give you, you're going to have the models already in the folders, already set up. But now we are always going to be, we need to make sure that the models are present, right? So this line of code here is just to check if there is any directory or if there is a folder called models. And within the folder, we are also going to check if. So if there is no directory called models, we are going to create it. So that's what this means. So this is kind of Linux. This is kind of Linux terminal programming. Now, if we're going to check if the file is there or not, right? If the file is not there, we are going to navigate to this models directory, which we are already sure that it exists. Because if it did not exist, we made it using this line of code here. So yeah, using this line of code here. So if the model file does not exist, what happens? We are going to download the TensorFlow model. And this is the path, or this is the URL to download it. So you notice that this URL lib here is the library that enables us to download documents or the model, as you can see here. So we are downloading the model from the TensorFlow website. You go to models and everything. So this is where the models are being stored. And you see that there are about 2 files here. Now, when you have already downloaded it, because when you download it, it's not going to come in a zip format. So the next thing that you want to do is to uncompress the file. So you want to extract the necessary information from within the file. So this is what this does. And you always know that when a line of code starts with an exclamation mark, it's kind of like a terminal command. And it's like you're executing it within the terminal. So this is not like Python code. This is kind of something in the terminal. Like if you were going to install something using, let's say, pip install matplotlib, you're going to have to start with this. So terminal commands are usually started with exclamation marks. So this here is going to extract this model that we just downloaded from here. Then when we have extracted it, we are now going to delete the zip file or the compressed file so that we don't have unnecessary documents or space or memory is not occupied uselessly. So when we have uncompressed the file and we have the extracted document, we now get rid of the compressed file. After that, we come back to our previous directory. So this here means change directory. So this is just to make sure that the models are available. And notice that there is this not here. So this does this only if the models are not available. So if the models are available, it will just return false for this and not execute. Will not create any models file. If it comes here and the files already exist, it's not going to do any of this. So in our case, when you run this, it's not going to actually create any of this because they are already existing. So now we run it and everything is fine. So the next thing we are going to do is to read through our class file. The class file is a file that contains all the classes, the object classes or object levels that are available. So as you can see here, we open the file and we split, because in the file, let me just go there and see if we can open the OK. So you can see that this is a list of all the levels that are available. And since we know in programming, when you're moving to the next line, we usually denote it by a \n. So that's why we are splitting it using the \n. So after every enter button is being pushed, we consider that as an item in the array. That's why you have unlabeled as the first item, person as the second, and bicycle as the third. And if you come here, you notice that it's the very thing. That's because we are splitting them using the \n. And here we print them. So these are all the available class levels in our file. So usually if the object is not classified as any of this is going to return unlabeled. So the next thing that we do now is to read our TensorFlow model, and OpenCV gives us this method here, which enables us to read a model. So OpenCV has this DNN. OpenCV has the DNN model, which is used to read a TensorFlow model and its associated config file. So this is a TensorFlow model here, and this is a config file. So they always move together. So the model file, this parameter here specifies the path to the TensorFlow model file, which we just downloaded. And the config file specifies the path to the configuration file associated with the TensorFlow model. So the config file will usually end with a .pb extension, while the model file usually ends with a .pv extension. So this function here, or this method here, loads the TensorFlow model and its configuration into the memory. So it creates a deep neural network representation that can be used for various tasks, such as inference on images or videos. So after executing this line, the loaded neural network is stored within the variable nets, and we can now use it for various tasks, such as object detection, as in the case of our project. We can also use it for image classification and any other computer vision tasks that we want to do. So depending on the model, we can perform specific tasks. So now let me run this cell. Now we create our detect objects function. So this function here, what it tries to do is to pre-process the image. So the function starts by defining a variable din, which is this, which represents the desired dimensions for the input image. In this case, it's going to be 300 by 300 pixels. And after having done that, it creates a blob. A blob is a binary large object. So it creates a blob from the input image using this method. So this method is part of the DNN module. So it creates a blob from our input image. And if you notice here, the input image is going to be this IM, which is going to be passed as a parameter to the function. And the parameters here include the scale. The scale factor here is going to be 1. Then we have the size. The size is basically the dimension that we pass here. Since we agreed that it's going to be 300 by 300, we have this bit over here. So we have 300 by 300, and we have the mean. The mean here is going to be simply 0. Then we have swap and the crop. So crop is going to be false. So this is going to pre-process the image. So here we are just trying to make sure that the image is the ideal format. An ideal format which we will be able to pass in the network. Because most models, they already have a certain configuration for the input. So if the input image does not align with what the loaded model is expecting, there's going to be an error. That's why when you have the image, you have to make sure that you process it so that it's going to look like what the model is going to be expecting. So when we have done all of this, the next thing that we are going to do is to pass the block to the network. So the network here is the loaded model. And we do that using the setInput method and pass the block that we just created. And after doing that, we now call the forward method. So this forward is performing a forward pass through the neural network. So this step generates predictions for objects present in the input image. And the function then returns the detected objects, which typically include boxes, confidence scores, and class level. So this forward here means that we are now trying to pass our image through the deep learning model. So the deep learning model is actually made up of layers and neurons. And to be able to make predictions on that image, before we are trying to find objects on that image, we need to make sure that the image passes through all the neurons or all the layers in the deep learning model. So that's what this forward here means. So when it does that, it's going to give us our predictions. And in our case, our predictions are the objects. And that is what we are going to return here. So we run this now. And the next thing now we are going to do is that we want to display the objects. Display the objects. So this function here is going to display the object. So we are going to try to locate the predicted object. Then maybe draw a circle or a rectangle about it. Then we also want to write the name because we remember that we had class levels. So when we detect an object, we want to give it a name. So it will be important that when we detect an object, we are going to try to write the name of that object by it. So that's why we have this. So we are just here trying to create the text. The text attributes or the text properties. So we have the text, we have this font face over here. The font scale and the thickness, they are the thickness. Then we are now going to use the text to create a black rectangle. And everything there, we are going to display the text inside the rectangle. So what this function here simply does is to draw a rectangle around the predicted object and write the name of the object. That's what this function here does. So if you remember in our annotating images tutorial where we saw the rectangle, how to draw a rectangle using the rectangle method, and how to write text using the put text method. So we run that. So over here, we are now going to try to apply our methods or make use of our methods. So here we are defining our font face. Font face is like the font family we are going to use. Then the font scale is set to 0.7 and the thickness is set to 1. Then now we now write our methods to display the objects. We write our methods to display the objects in this method here, or our function. Sorry, it takes 3 parameters. Then we have the objects. The objects are the predicted objects. So the objects that were predicted by the model. Then we have a threshold. A threshold value is now used to filter out objects with a confidence score below a certain threshold. So what the model does is that it predicts certain objects on the image. When it predicts a certain object on the image, it assigns a confidence score. A confidence score is like the accuracy with which it is predicting that object. For example, if I have an image with an apple on it, right, and the model returns apple, and the confidence score is, say, 0.9, because it is in percentage, let's say we have 90% confidence score. It means that the model predicted with a high amount of surety or high amount of confidence that the object is an apple. So the higher the confidence, the higher the accuracy. So this threshold here is just going to be used to filter out the objects that have low confidence, because there are some objects that are a bit complicated to identify. So the model will try its best to identify it and give it a class. But the fact that it has given it a class doesn't mean that it is what it is. Because in some cases, it might identify your head as a ball, right? Because if you want to look at it critically, you're going to notice that your head has almost the same features with a football, whereas they're not the same. But the computer or model is going to predict your head as a ball and might attribute some confidence level of 15%. So you see that that is quite low. So that tells you that the computer is not really sure of that particular prediction. So that's what this threshold here is trying to say. So our threshold here is going to be 25%. So any prediction with a confidence level of below 25% is going to be rejected. So that's it for the parameters. The next thing is that we want to create this function here, and this function iterates through each detected object in the object arrays. That was this object array was returned by the detect object method. So we are going to iterate through each object in that array, and we are going to retry the class ID, the confidence score, and the bounding box coordinates. The bounding box coordinates here are like the coordinates that are going to be used to draw the rectangle around that particular object. So if the confidence score is above the specified threshold, it displays the class level of the object using the display text function defined earlier, and will also draw a rectangle around the detected object. And after all the processing, and like after I process all the detected objects, the function now will convert this function here. This convert color function is going to convert the image from BGL to RGB. Because remember that OpenCV works with BGL, but usually we work with RGB. So it's always important to convert it to RGB so that we can actually see the actual colors that are there and not some kind of inverted color. So this function, now we run this cell, then we now try to test our functions. So what happens here is that I'm going to run this. Okay, nothing happens here because we have the object. We have the input image. So we have read the image and we have our object. So we pass the image to the detect object, and if we remember clearly, the object is going to be processed, then passed through the model, and is going to return an array of objects. So we have these two. So now we are going to pass the image and the objects to this function that we have created here. And when we run, we have this. So this is a picture of some people crossing the road in some random city. And you can see that almost all the objects here were identified. These are the objects that had a confidence level of above 25%. I notice that the majority of them have been well predicted. Like you have this guy. This guy has been predicted as a person, and as a person, you can see some cars here. You have cars, then this is another person, a car, another person, and everything. So you see that QTune does a very good job. So let's see what happens if we were to modify the threshold value and see which other object will be added. So if I come here and I take it to 0.15 and I run this cell and I return here and I run the cell again, what happens? You see that I don't really know which added. So let's try to increase the threshold. Let's increase it to 0.75 and 75%. So the ones that are going to be detected are going to be actually very accurate. So let's try. Okay, now you see that the number of objects that were detected are less. So these ones are the ones that were like the computer was, or the model was very sure. Like the model is very sure that this is a car. The model was very sure that this is a bicycle and this is a person. So when the threshold value was 0.25, it correctly identified this guy here as a person. But when we increased the threshold, it didn't. So we might presume that, okay, his face is backing the camera. That's why the computer wasn't that sure. But with this guy here, he's like facing sideways. So at least you can see part of his face. So even though the level here has some kind of covered part of his face, it shows that his face is actually a bit visible. So let's take it back to 0.25 and run, and let's try another example. So this is a baseball here. So let's just try to take a look at the image first. So this is the image here. So we are going to try to predict the object in this image. So let's move back to we have this, and let's run. Okay, So over here we have identified this guy as a person. He also identifies the glove as a baseball glove. Yeah. We also have the sports ball, and you have a baseball bat. And this guy too was identified as a person. So we see that it's quite accurate, and there are some cases where there are false alarms. So if I was to run this cell, let's just take a look at the image. First of all, we have a soccer. This is a picture of Neymar on the pitch. Right, so let's see. If I also do this and run this cell. Now you can see it identifies Neymar as a person, but it has identified his boot as a sports ball. This is another sport ball. So you see that the model has wrongly classified his boots for a football, shows as a sports ball. So let's try to increase the threshold value and see whether we can remedy that situation. We head back here and I run. Let's see. Okay, it still classifies the boot as a ball. Wow. It shows that the boot has a lot of the features of a ball. Let's increase it to 0.75 and see. It still classifies it as a sports ball. Let's keep on increasing the threshold. Okay, now you can see it has disappeared. So it actually tells us that the feature of the ball are very similar to this part of the boot, because this other leg here covers this part, covers the boot. So here actually looks a bit round, and the model wrongly classified this as a sports ball. So when we increase the threshold value to be above 85%, this was removed. So that's an example of increasing the threshold value to be able to be sure of which objects were actually correctly classified. So this is all about the projects. And this concludes our OpenCV tutorial series. So you can always look at the projects again, understand the concepts. And yeah, the project involves many concepts because we are talking about a model. We are not the ones that built the model. And that is how it is going to be most of the time. Because if you're going to master the OpenCV library, you must not necessarily know how to build a model, because that is now deep learning. But you should be able to use a model that has been built by some organization or some other developer and be able to incorporate it with your computer vision skills and use. So you can always try to get a video of yourself and apply this model to it. Apply the model to a live video. So you can be taking a camera, you can be taking a video of a certain area, and each frame is being passed to the model. A sword is going to predict the objects in the video in real time. So you can always make some changes, experiment, go wild. And the important thing is to make errors, learn from them, and become stronger. So this is all about our OpenCV tutorial. I hope that you have actually learned a lot from it. Remember, it is a video. You can always pause, go back, and reduce the play speed. The important thing is to make sure that you understand the fundamental concepts of OpenCV. See you next time.